Okay, there's still people coming in, but I think we'll start because it always goes longer than I think it will, right? All right, so we're going to talk about quadrupolar nuclei today and tomorrow. It's like an elective topic, like it has nothing to do with any problem sets, although I always have to pepper little exercises into my lectures, but it doesn't have anything to do with the assigned homework. It doesn't have anything to do with the exam that you already have. And it's going to be just a fun, separate topic, give you some ideas of things maybe you could do. And we're really lucky because Eric, he'll tell you about his background, but he has a lot of experience with advanced quadrupolar experiments of a sort that could have really nice applications in biology. So I'm going to just do some introductory remarks, and then I'm going to turn it over to Eric. Remarks meaning 60 slides. Some remarks. Okay, so the idea of thinking about quadrupolar NMR is to open up the periodic table a little bit, right? Because it turns out that there's just a handful of spin 1/2 abundant stable nuclei. Yeah, I ran here also. This time I didn't take the subway because then you do the Stairmaster. I decided to just run from my house, and this is not my running out. Okay, so two things that are both true when we move to a quadrupole instead of a spin 1/2. One is that with the larger spin quantum number, you have a more complex set of spin matrices. And we're just going to have to get comfortable with that. They may behave a little bit differently. You may have a few new coherences that will need nicknames and things like that. But the more important maybe is that for every nucleus that has a spin quantum number greater than 1/2, you have a new interaction, which will pop into your Hamiltonian. It's large, it's local, it's anisotropic. It can be very informative. But the thing is that for almost every case, with just a few exceptions, it's more complex geometrically and mathematically than what we're used to. And so it's actually an active area of research still. I mean, there were some amazing things that came out in the early 90s, but then after that also, and still coming out today, how to capture the potential of these NMR experiments to get narrow lines and interpretable information. Now, these two things seem like quite distinct things, right? You have more levels and different spin matrices on the one hand, and then over here you have this new anisotropic interaction. But they're lockstep, and it is something that's provable, that while I equals 1/2 has a magnetic dipole moment, this higher moments in the multipole expansion for the magnetic properties are strictly 0, and there are no non-zero electric moments. So they're lockstep, even though they seem like, okay, those two things are completely different complexities, but they go together. And it's always interesting to think, this is going to be unsatisfactory a little bit, but it's interesting to think which nuclei are going to have which properties. And I don't know, because you were educated at the undergraduate level somewhere else. I don't know what they might have taught at the general chemistry level. Here in the United States, we skip the chapter on nuclear chemistry for the most part. And so we don't learn this stuff. And if you go and battle the topic, it turns out to be pretty complicated. But we could say a few things about which nuclei can be measured, which have a common isotope that's NMR active, which are going to turn out to be spin 1/2, which are going to be even integer spin versus half integer higher spin, which are different in ways that we're going to talk about today. So I borrowed two periodic tables. This one is from Sharon Asper. This one is from Phil Grandinetti. And they're emphasizing something about patterns in the periodic table that you can anticipate. So one is on the right, just thinking about Z, the atomic number. When it's even, the most abundant isotope is not NMR active. Bad news. But a minor one might be. And if a minor one is NMR active, then with odd number of neutrons, so it would be an odd mass number overall, it would be half integer spin, even number, even mass number, integer spin, which is typically not a good thing, with just a couple of exceptions. And then on the other hand, if you had an odd atomic number, the most abundant isotope is almost always NMR active. And since it has an odd number of neutrons, or sorry, if it has an odd number of neutrons, then it would have an even mass number overall, and you're going to end up with an integer spin system. Even number of neutrons, odd mass number, half integer spin. So the one from Sharon Asper emphasizes a different thing, which is like, I don't know, I feel like it's a bad message for today's lecture. She's trying to show you where you're going to get those spin 1/2s. That's not what we're supposed to be hungry for today. But it's determinative, by which I mean, once you know that something's spin 1/2, all of a sudden that has lots of consequences that tend to simplify things. And you can just think about everything you've learned about for the proton. So that's where it's like this lavender color. And if she gave you a rainbow, that means that there are various isotopes, and there among them, there somewhere in there, there's a spin 1/2 that people have managed to measure. But the thing is, from the rules we were talking about on the last slide, you can see that if the sum is odd of the number of protons and neutrons, that it might, there's some chance it might have spin 1/2, and how would you know? For that, you go a little deeper and think about the nuclear shell model. One of the features there, a really important foundational assumption, is that the protons and the neutrons, both fermions, they get paired separately. All right, so the mass number is somehow interesting to find patterns, but the physics is at the level of protons pair with protons, neutrons pair with neutrons. So this model was developed in the mid-20th century, partly in analogy to the Bohr model for electrons. And there are a number of people who contributed, but two who got the Nobel Prize for this topic is Hans Jensen and Maria Guckert-Meyer, who worked at Columbia for a while, but I discovered that Columbia didn't actually pay her. She left and worked at Chicago and had a much better time. That's a long time ago, but you know, it's the constant of the motion. And also Wigner of the Wigner matrices, and he won a Nobel Prize for a broader topic. Now, in this model, you have these things called magic numbers, and that it would be a value, for example, for Z, the number of protons, when you have a completely filled shell. So it's a shell type model, right? And if it's filled, all the spins should be canceled. So these special numbers correspond to elements for which you have a ton stable isotopes. Z is to 820, 28, 50, which is helium, oxygen, calcium, nickel, tin, and lead is a great one. This is so deep in the periodic table, and it's got like all these stable isotopes that people can use to identify where it came from in the world. Like it's like a barcode. Like how much do you have of, you know, each isotope tells you that it's from South America or where it is. So you have tons of stable isotopes for these magic numbers, and it's a filled shell, and it should have 0 spin overall. And that model works pretty well. If you want to dig deeper, you'll have to definitely talk to somebody else and be ready for some complexity. But if you go to low Z elements, it's pretty intuitive. Just the one proton, spin 1/2. You have 2 nucleons, but they're of a different sort, so you don't pair them, right? And you have spin 1. And it has 3 levels, kind of like a triplet. And for tritium or for helium-3, either way, you have a filled shell, a magic number of 2 on one side, and then an unpaired. Helium-4 is doubly magic, they say, and it has 2 protons, 2 neutrons, and it's I equals 0. So far, it's like super intuitive. And then if you go into the first row, when we talk about orbitals and we teach general chemistry, you get through the first row without breaking any rules for the most part, and then it's the third row where I'll help. Well, here it's already like in the first row, it's just, okay, but the second row, I had high hopes, but it's already a little complicated. So 6, people ask the question, you can see discussions in physics for, is 6 kind of like a minor magic number because carbon 12 has got I = 0, and there are no good answers for that. Or you go to oxygen, which I hope we're going to learn a lot about today and tomorrow, and that is doubly magic, like helium-4. It's got 8 protons, 8 neutrons, very abundant, or not very abundant, it's the primary abundance one, and it's I = 0 as per your expectation. But O17 is important for us. We want to measure oxygen. It's our first opportunity to do so. You're just going to add the 1 neutron on top of a doubly filled shell. So silly me, I was hoping for a spin 1/2, right? No, there's orbital angular momentum or something like it. So anyway, it's 5/2, and that will be hopefully one of the opportunities and examples we'll learn a little bit about. Yeah. Oh dear, he has a question. Don't ask me questions about this. No, go ahead.
I was just wondering if anybody has, if a physical model for gyromagnetic ratio has been.
Well, I know somebody who works on that. So at the level of just dropping names socially, I can answer that. We have somebody here who is actually concerned with the deuteron as being an open question. And to which I said, I'm going over this. This is back when I was a dean, and I'm like, that's a question. We don't already know the answer. Wow. And yeah, so it's the fine structured constants and the aeromagnetic ratios are high energy physics active topic apparently. Okay. So I'm going to talk about what I consider a little bit easier half of the topic first. And I'm going to do it in a kind of warm up as we did for spin 1/2 and the CSA and 2 coupled spins 1/2. I'm going to start with some notation that refers to Cartesian coordinates, and then we can think about how that would parlay over for spherical harmonics. Okay. So let's just back up and remind ourselves about I. If I is non-zero, this means that the nucleus possesses spin and magnetic moment. I represents the quantized total intrinsic spin angular momentum, a measurement whose expectation value is that there. And I think the most important thing about saying what I, like 5/2, 2, what I is it? I think the most important thing about that, the defining characteristic, is how many levels are we 2I + 1 quantized eigenstate. So spin 1/2, 2I + 1 is a 2-level system, right? The next step up in complexity would be I = 1. 2I + 1 is 3 quantized magnetic energy states. And there are several examples that are of interest or practical importance. So we're going to talk, to the extent that I have examples here, mainly about deuterium. I = 1. And we use that a lot in chemistry and in biomolecular structural studies. Why do we use it? Sometimes to remove proton couplings. You sub in the deuterium. You're doing that because it has a lower gyromagnetic ratio. You didn't really want I = 1. That's not why you picked it. You're just picking it because it has a lower gyromagnetic ratio. And then you don't have the spin bath concept quite as much because the couplings between 2 deuterons are knocked back by the square of the ratio of gyromagnetic rate. And so that's like more than an order of magnitude, almost 2 orders of magnitude. So that's good. So you're getting rid of this complicated coupling bath. But there's another reason we like deuterium, and that is that its spectrum is dominated by a single interaction that can be approximated as a second rank tensor with a normal second Legendre polynomial. So it became very, very popular for dynamic studies. So its CSA is so small, and its couplings to other things so small. So you just kind of have this only one local term on top of the Zeeman, and people love to study dynamics using the deuteron. Also, it's just got a right-sized quadrupolar coupling, so it just about fits into the spectrometer in terms of like, it's not too broad, but it's big enough that it dominates everything else. So it's like Goldilocks kind of nucleus. Yes.
I'm little curious because I see this in the literature quite often about how smacking a spin one nucleus next to a spin half affects spectral properties of that spin half
Yeah.
in unexpected and artifactual
Yeah.
spin nucleus.
Yeah.
How does that work?
Yeah. I had a comment later that often the relaxation properties of the spin one will be pretty efficient, pretty strong relaxation. And so the couplings are often not visible. Now, that doesn't mean that they have no consequences. They can contribute to the relaxation of the parent atom. But you might not see those resolved couplings. It's not quite your question, but I'll point out another one that's sometimes the most important thing in chemical and biochemical applications, which is that there's an isotope effect on the chemical shift of the parent atom. So that can be confusing if nobody warned you about it. So you might miss out the J coupling. The dipole coupling might have a kind of broadening mechanism on it. And you might have an isotope shift. And
How Krushelnitsky's literature talks about wider distortion. These exchange spectra experts. I'm not sure what is.
Yeah.
I'm not sure I'm making myself very clear right now.
Yeah, maybe we actually get out the paper.
Yeah.
You want to bring it to make sure I'm answering the right question?
Sure.
But I think those are the primary things that we first expect. And so if you have a shift, a new relaxation mechanism, then depending on the strengths, you might need to add that to your simulation. That's the first thing that comes to mind for me. Okay, so I was just talking about it being a kind of right-sized quadrupole. This was supposed to be before that when it's out of order. This was just pointing out that for I equals 1, it's a 2-level system, and which for I equals, sorry, it was supposed to be before this. All right, so we're doing I equals 1, and we might begin with state vectors. These are eigenstates, and so the vector might be the amplitude of each of these eigenstates. But as you know already, we do all our calculations with density matrices, not with state vectors, but just to start with a basis set. You can see already that it's not the Pauli spin matrices. It's not just 2. You need obviously 3 amplitudes to describe state of an I equals 1 spin. So L, M, but L is always 1, and M is 1, 0, or -1, representing the projection of that spin 1 along the measurement axis, which is almost invariably the magnetic field. So with that convention as the eigenstates, we can think of what the measurement operators should look like. And they always have a partner density matrix. And sometimes people use those names interchangeably, just like for spin 1/2 or 2 couples spin 1/2. So measurement along Z. Sometimes that's the easiest one to start with. It's going to be a diagonal matrix because our basis sets are eigenvalues of the measurement along Z. And so nothing off the diagonal, the measurement for the interstate is 0, and then the outer measurements mentioned already. So 1 and -1. So that's the easiest operator, an operator and density corresponding density matrix to derive. Here's another one that's a relatively easy one. So thinking of the spin operator I as being a vector of Ix, Iy, and Iz. And the dot product of I on itself, giving you IX squared plus IY squared plus IZ squared. That's always our unit matrix. It's just one. The only thing to comment here is the scaling of it, that we want that to be the measurement of the total spin. Then it should have an amplitude or a norm that is larger than 1. So it's going to be I plus 1 or I squared. So that's not a feature that you see. Well, I guess it has this analog for spin 1/2. I was going to say it's not a feature you see for spin 1/2. It's not strictly true, but this normalization of the matrix is important. So we return the right amount of angular momentum, both for I squared and also for IZ. That you return, for example, this is normalized in the sense of the physics will be right, that a transition from this state to this state will differ by exactly 1 unit of angular momentum. So we can't just scale these arbitrarily. That's what I'm trying to say. So I squared is I plus 1 times the unit matrix, which will turn out to be true for other spins as well. We're just doing I equals 1 right now, but that'll be. Now, we do expect to find another operator that's purely diagonal. When we had only a spin 1/2, we had the Z measurement and then we had the unit matrix. Those were all the diagonal matrices. But here we should have a third one because there are 3 entries on the diagonal. And that third one has to be orthogonal to the other 2 and also normalized properly. And it turns out to be this matrix. So that can be rewritten as I squared minus 3 IZ squared. And it's a matrix that is distinguishing the inner and the outer layers. It's even with respect to M. So an outer layer returns 1 number and an inner layer returns a different number. It's a really important matrix in this spin space because it'll turn out to represent the new Hamiltonian that we're working with, the quadrupolar Hamiltonian. But just for the moment, we would have just obtained it by saying, we got to have another diagonal one here. What is it? So we had one that was a unit matrix, one that was anti-symmetric, and this is our symmetric one. And now we have all the populations in this space represented as density matrices. Now, the coherences, I don't know if you remember. Yes, please.
The previous slide you had in bold saying that they represent population.
Yes. When that's a density matrix. Okay, so these matrices are going to be used in two contexts. One is as a density matrix representing the state of the system. The other is constructing measurements and Hamiltonians and yeah. So as a density matrix, if you stay on the diagonal, that's population, right? It's CI star CI. All the populations can be broken down in terms of, well, unit we don't care about, a Z-type population or a quadrupolar order is the lingo. Something where the outer layers have, outer states have one population and the middle state has some different populations, so called quadrupolar order. All right, now coherences. So do you remember how you made X and Y coherences with the Pauli spin matrices? So I usually think about it as linked to these raising and lowering operators. And main reason of thinking it that way, you can construct it in other ways, but the main reason for approaching it that way today is that you could use this approach for any spin. Now, if you say that I was going to do a homework set and it's about I equals 7/2, you could actually pretty easily make your X and Y. It wouldn't be a big job. So X has a relationship to the raising and lowering operators and does Y. Okay, so if we know how to write the raising and lowering operators, we can write the X and the Y. Density matrix for the to write the coherence as a density matrix, or to write a operator that means I'm measuring along X, either one. So these are almost foundational definitions of what raising and lowering operators do. And with that rule, we can write the matrix just by inspection, right? So if, let's say, initial state would be this index, final state would be this index. So I start on it. I just did that back here. And yeah, let's do the other way. Initial state, this index, final state, this index. So I'm already in the highest state, so I can't generate anything out of that, so I enter a 0. Initial state is the middle level. Final state is the top level. That's an entry for the raising operator. That's something the raising operator does. And the number I should put in there is computed knowing I, which is always 1, and M for the initial state. And it always generates for you something which has M, the next value up. So again, if the initial state is already the highest level, it can't generate anything. The initial state is the middle level, it can generate the top state. If the initial state is bottom level, it can generate the middle state, and everything else is 0. And it's just normalized by that group of I and M. Good. So those are your raising and lowering operators, and then you just need to manipulate them to generate IX and IY. So IX is made from just adding them and normalizing by 2, and IY by their difference, but it's also complex. Okay, so we have our I, X, and our Y, IY. Now, if you think about this 3 by 3 matrix that represents all possible states of the system in the density matrix, there are actually 4 entries that are just one place off of the diagonal. And all entries that are one place off of the diagonal are single quantum coherences. They always represent that physically. So I need to find 2 more single quantum coherences besides X and Y. They're out there somewhere. What could they be? And we know that they have to be perpendicular to the 2 matrices that we just generated, right? We generated this and this. And one of the properties about both of those matrices is that whatever I see here, I see the same thing here. And what that means is that if I like, and this is going to come up several times in the lecture, if I like, I can think of this as one subspace. And it describes a level pair. And it's not okay to take that out of this matrix without further thought. But we can just say, okay, that's a subspace within this matrix, and it represents like transitions you could have in principle between m equals 0 and m equals 1, right? And this subspace could be representing transitions from m equals -1 to m equals 0, all right? So whatever I'm generating in this subspace, I'm generating the same exact thing here, right? And that's also true for this expression for IY. What I've done in this space, identically here. The other 2 coherences are going to have a funny property that I would make something like X here, and I'd make -X down here. So they're anti-symmetric when we think about the 2 subspaces or the 2 transitions. So IQX looks kind of like IX because it's not imaginary and it's symmetric about the diagonal, but now I've flipped the sign for the lower subspace. IQY similar. You want to think about that for a minute, look at it, if you have a question.
I can break down IQ into plus.
Yeah, I mean, later on we'll look at spectra, and if you think about 2 lines represent those 2 subspectra, they're literally pointing opposite directions in the XY plane. And we'll come back to this point again, but you can't get anything in your receiver from that. It just adds up to nothing in terms of induced voltage or projection on I plus is 0. Other thoughts, other questions about these two new? Without the physical insight though, can we just say, I think we've spanned the space now. We had symmetric versus anti-symmetric for these 4 numbers. In terms of top and bottom, and in terms of above, below the diagonal. So there can't be anything else that's perpendicular to it, right? Span the space. You happy with it? Okay. So we covered the diagonal entries, we covered the single quantum type entries. What's left? That must represent double quantum coherences. There are 2 left because we constructed 3 populations and 4 single quantums. So we constructed 7 things now. And we have 9 entries, so we better find 9 matrices. But also we know that we never use these 2 entries, which physically must be double quantum. So even though I'm doing this Cartesian, we are still trying to think about organizing things the way you do for the spherical harmonic. Now, there are 2 double quantum operators in the way that they are conventionally put together. As you go on to these higher spin systems, you can see different conventions in different textbooks, right? So if you wanted to, and I think Malcolm Levitt does something like this in his book, and I'm not quite sure why he's doing it, you can just call this one of them. One of them is just the guy down here, and the other one is just the guy up here. And those are perpendicular to each other, and you expand this and so on. Here we made a double quantum coherence. It turns out to be equivalent to ix squared minus iy squared. So when we take products of x and y, we generally make either 0 or double. And this particular combination gives you double quantum type coherence that is symmetric across the diagonal. And then to make something that's anti-symmetric across the diagonal, it looks a bit like an XY, but in order to get it to be purely double quantum, I had to take out a copy of IZ. I don't know if there's a better way to do this. I just did this way to complete the set. And then you have an intuitive, like symmetric and anti-symmetric combination. So those are all of our potential operators or potential coherences. It's a basis set for them. So I did a kind of mishmash of just like trying to make something that's independent linear algebra, trying to think about physically what it might mean, and trying to just keep multiplying stuff until I don't find something new. And you could have a different path there. Probably a very useful thing if I were to remake this. I had to remake my notes on this because I hadn't taught it in so long and everything was corrupted. But if I had to remake, like if I lost it again and I had to remake it again, I think instead of doing what I just did, or if I were to give you a homework problem about this, I would probably have you start with X, Y, Z, and maybe one other, and see if you just make commutators over there. How much of the space can you fill? So you obtain some of these very naturally as a commutator between two other coherences in the space. And a really useful thing, if you're going to do a lot of problems with this, is to consider all commutators. So this is now a 9x9 matrix, but it's something that you can do it once for all time. Anytime I see the commutator between the double quantum order and the quadrupolar order, I know it's, so you just have this, as a cheat sheet for all time. If you're going to work with that spin, sort of nice thing to be aware of. So we probably could have constructed it that way instead. Just work on that 9x9 matrix until we've got every entry. But however you construct it, I did it in some strange mishmash way, but however you construct it, it is good idea to confirm that they are all mutually orthogonal. You remember how you would do that? Yes? No? Yes? Hmm? You could do that, but I just mean if they're orthogonal, I just mean that if you multiply them, the trace should be 6, right? And they should also be normalized in a useful way. They should, I already said this on another slide, but they should return or predict the correct amount of angular momentum for the eigenstates, like the differences along Z. And these matrices do not have a norm of 1, they have norms of 2. And it would maybe be a good idea to just check that they're all the same. Like whatever the norm of Ix is, I would hope Iy would be the same, whatever. So those are checks that you could do. All right, in addition to the coherences and operators for constructing Hamiltonian measurements, we do need rotations as well, and we constructed those before for the spin 1/2 case as follows: the exponent of the corresponding operator. Like a rotation around Z is an easy one. What makes it so easy is that it's a diagonal matrix, and so you can just exponentiate the entry. The entry is 0, you get 1, otherwise you just get normal sinusoid. That's really easy. If you want a rotation about X or Y, then you have to do what we did for spin 1/2. You can take a Taylor series expansion, or you can diagonalize it. And you'll get a more complex, less elegant and intuitive outcome. But you should get a unitary matrix. That's how you would check your work then. You generate it and then you check it by making sure that it behaves geometrically correctly and that it doesn't make your vectors any longer or shorter than they started. So now that you have all of these matrices, you could construct the Hamiltonian and you could describe an echo pulse. And I'll say this about 4 times during the lecture, but the echo is something it's mentioned a lot because it's important for broad line NMR, and these are going to be broad spectra that we're going to talk about. So with an echo, you want strong, ideal, short pulses, perfect hardware, and that way you can avoid the ring down and the artifacts at the beginning of your measurement. Because with an echo, the first point you digitize is in the clear long after the last pulse, right? That's what's so important to solid state NMR spectroscopists about understanding echoes. So we're going to be talking about echoes. Now, but before we do that, we have to talk about the second difference for quadrupoles. We talked about that the spin space is different, so we have to construct those matrices. We do that. But we have another term in the Hamiltonian is a new term that is anisotropic, potentially informative, potentially challenging, and it's not magnetic, it's electric. Which is not really given away by its name. If I say something is a quadrupole, it just means I did an expansion. It doesn't tell me whether it's gravitational or the weak force or the strong force. It's a strange name that somebody gave to it. I'll just name you by which order of the expansion you came from. But it's electrical. We're talking about electrical interactions. So it is a true fact that any nucleus that has a spin that's greater than 1/2 has a non-spherical charge distribution. And if it's spin 0 or spin 1/2, we don't have to worry about this. But if the spin is greater than 1/2, integer or non-integer, the charge distribution inside the nucleus is non-spherical. So if you think about that expansion, monopole, it just means like the charge, like how much charge is there, approximating it as if it were spherically symmetric, and it's never going to be experiencing any torques because it doesn't matter if you rotate it, right? No torques. The dipole, we always say it doesn't exist. And the way I think about this, it's not very profound, but if I had a dipole, I could just pick a different center of mass for the charge. If there's no reason it should have a dipole because it's all positive charge. So just if you find that you have a dipole, you're not at the center. You picked the wrong center. There's no dipole, but there could be a quadrupole, and that is asking the question: is my distribution chart of charge a little bit cigar shaped or a little bit frisbee shaped? That's the question the quadrupole always asks. So if you think about your orbitals, p orbitals are not frisbee and cigar shaped. They're like anti-symmetric. The s orbital is not, it's spherical. But the d orbital could be like the one that we like to draw as dz squared. It has like a ring and then it, yeah. Z is different than X, which is the same as X, it's the same as Y. Okay. So there's a parameter, the nuclear electric quadrupole parameter, Q sub I, with units of area or barns. When it is 0, it means spherical, so there's no quadrupole. Okay. When it's less than 0, that means it's like a frisbee. And when it's greater than 0, it means it's a cigar. Shape of the positive charges. And if you scale that parameter by the elementary charge, then you have what we usually talk about, nuclear electric quadrupole moment. We'll be talking about that moment regularly with the chemical point. This is invariant. We're not going to do anything to the nucleus to change this property ever. I think you'd have to go to like a black hole or something. I don't know. You have to go to an excited state, which is not about to happen. Temperatures, gamma rays, or I don't know what. So it's always going to be the same number. You could get it out of a table to the accuracy that you need. The thing about the charge being non-spherically symmetric is that it may have a preferred rotational orientation inside your molecule. And that's because of one particular property of the molecule. Molecule has an electric field gradient. So if you had electric potential, which is what we're often calculating if we want to talk about energies, then you might have a field, which is kind of generated from the potential by a derivative. And the derivative, and that field, would point you to where you want to move. But the second derivative of that field, an electric field gradient, would interact with the quadrupole to instruct it how it might like to rotate. So just like when we talked about magnetic properties and RF pulses, we're not talking about translation of the nucleus. We are not talking about rotation or translation of the whole molecule. Imagine all that is sitting still, and your nucleus is on a gimbal mount. It's just rotating in place. That's the torque I'm talking about. Just make the nucleus face a different direction. And the thing that will cause it to want to rotate is the electric field gradient, which is often given the symbol V, but sometimes is given the symbol small q times the fundamental charge. I thought that was on this slide. It must be later. So there are other symbols people use for this. I think this is the most unambiguous. It doesn't look like any of the other symbols I'm using. So now it has two spatial indices because you took two derivatives, and you could take the first one along x and the second one along y or whatever you want. So that's a classic second tensor. Looks a lot like some other tensors we've talked about. All right, any questions about that?
Also, this field gradient is
How is it generated? That's a bonding electrons and maybe some other nearby electrons. Oh, I think it's on a slide. Let me just see if I can put the right slide up while I'm answering that. Yeah. Okay. Most nuclei in molecules, if it's not an isolated atom, right? It will have an electric field gradient. It just means it's not centrally symmetric. It's not a symmetric system. An isolated atom, forget about that because it probably, many of them, not all of them, but many of them will be symmetric. But let's say you're in a molecule, you've got a bond, okay? So you look this way and you get one electron density. You look that way and it's something else entirely. If you're a deuteron in a CD bond, it's probably axially symmetric, the electrons around you. There's something unintuitive, which is that nearby charges, like a hydrogen bond for your deuteron, can have a surprisingly large effect on the gradient right at the nucleus, which is sometimes called core polarization, sometimes called the Sternheimer effect. So your intuition just to say, oh, it's a p orbital different, and it's not always certain. So this is something you really want to calculate with ab initio tools or with any kind of orbital calculation that you could do, and then calculate that gradient explicitly, and some aspect of it might be a little bit non-intuitive. But it's definitely a probe of bonding. As you change the bonding, you will change this gradient, and so you can compare models of your molecule to your data and learn something for sure.
I mean, how does this nucleus spin quantum number affect?
No, doesn't affect it, just interacts with. So these are electric interactions that have rotational dependence, because the quadrupole inherently has a rotational dependence. So as you rotate the quadrupole sitting in a field gradient, the energy will vary. So that anything that behaves that way will generate a torque on them. But they don't influence each other, I would say. Or that influence would be very, very weak. So the quadrupole of the nucleus, we consider that a constant for all time. And the field gradient is mainly changed by changing bonding.
I mean, if I take a 1/2 spin half
Mm-hmm.
versus a quadruple,
Mm-hmm.
how does this electric field vary?
It's going to be there, but the thing is, it won't interact with the nucleus to generate this torque, because the nucleus is spherically symmetric. So the nucleus can face any way, any old which way in terms of this electric interaction. It would make a bit of difference. But that field gradient would still be very similar. Okay, let's say proton versus deuteron. It's going to be an isotope, but it's going to be small. Right? So they'll have the same electric field gradient. But in the case of the proton, it doesn't matter, because there's a spherically symmetric nucleus. So he doesn't care. He doesn't care about that field. It doesn't make a bit of difference to him. But for the deuteron, as its nucleus has a shape factor, it's going to want to line up a particular way in that field gradient. So it matters for the deuteron, it doesn't matter for the proton. Does that make sense?
I was just noticing that the potential is a well-behaved continuous function. So the field gradient tensor becomes symmetrical on the right.
It will be diagonal, but not necessarily uniaxial, but a lot of them are uniaxial. Like, let's say it's an OD bond. This is actually, there's a lot of paper stuff. It's an OD bond, but that D feels a hydrogen bond to something else. So that broke the axial symmetry. It changes the principal value by a way that you can fit to a line. And it also introduces an ADA, and there are these beautiful papers from like 70s, 80s, whatever, where they do a bunch of compounds and they show you what happens to ADA and delta. But ADA is usually small for the cases that people do deuterium atom bond. Not necessarily, I don't think, for, cases that you'll hear about later, like what Eric might show you. Okay, so there's a torque on a nucleus, and it's because of its electric characteristics. But you remember in high school physics when they taught you to really think about net force. Don't just think about one force and another, right? You have these pseudo forces and whatever, and those problems where people are rolling things off of tables, and they always say, well, what's the net force? And here we need to think about the net torque, right? Torque being the analog of force. I don't care if it was electric in nature or magnetic, we just simply have to add both torques, you add them. And that's how these two very different things end up in the same Hamiltonian together. So when a nucleus rotates due to the electric quadrupole interaction, the magnetic moment is going to rotate too. When you rotate the nucleus due to RF pulses or precession magnetic interactions, you will be rotating the electric properties too. So these are internal these are properties of the nucleus which derive from an internal structure and carry the same coordinate system with them when they move around.
So,
Yeah.
Can then the CSA interact? These two dimensions.
They can interact, yeah, but I don't think it's a very common cross term. No. No. You know, the cross terms that we see, we add them up in a Hamiltonian. That's what you're gonna see. You're gonna see that I add something from the CSA and I add it to something from the quadrupole. In rare cases, we do have to multiply as if they interacted with each other, but that's not a good example of that. When we multiply things, it's usually because it's a different topic. It's not today's lecture, but I'll just answer your question. I'm a nucleus. I'm coupled to someone else. As I rotate the whole molecule, my partner not only changes R, the usual reason for dipole coupling being anisotropy, but because it's getting rotated differently, it actually is going to change the strength of that spin, its orientation. These are situations that are not high field limit. These are complexities that come up if I'm coupled to a very strong spin like an electron. And that electron does not feel like B naught is the biggest thing ever. Okay, so you can have funny situations where you multiply these interactions on each other. But most of the time when we talk cross-correlated for solution NMR or combining, it's just, you just add them. They're just torques and you just add them, or they're just energies and you just add them. And I think that for the two you talked about, that's probably a fair answer, just add them. All right, but what I was gonna say is, all right, so the torques this, it really doesn't matter who pulled on it, all of the measurements will come together, and therefore, when we write the Hamiltonian, we're gonna do something that is actually funny, and I don't know if when people are reading these, they find it confusing. I did the first time, and then often they don't stop and comment on this. We're going to represent the electric quadrupole moment as the outer product of I, but I represented the magnetic properties, the spin. Wrong property, but it doesn't matter because the electric properties are tied to the spin, and this notation is a massive convenience. So you could say, well, how do I know the quadrupole is, in some sense, Z is the same Z? But I guess it comes out in the wash. You know, you're constantly tying them in the same way, it comes out in the wash. So we talk about spin degrees of freedom for a quadrupole interaction, even though we're talking about electric quadrupole. So throughout, I'm just saying this so many times because you see that you read a textbook and this point is not made very strongly. They just call it a quadrupole as if who cares what kind of a quadrupole, and then they represent it by a spin, and then, you know. But it's the same vector can be used, taking an outer product on itself to create something of the proper rank, second rank, right? It's not a dipole, so it shouldn't be just I. It has to be I outer product with I. That represents an electric quadrupole, even though you made it out of spin measurement. So it's I outer product I, and it's second rank. Sorry, I should have had the. Okay. So our Hamiltonian in general looks like I dot into the field gradient dot into I. Those are the things that have spatial dependence. But just as we did with the dipole and the CSA, you can gang those two I together, make a second rank, and the V, and then make a dot product out of those two. Remember that? And then you can convert them both into spherical harmonic, and then you can read a paper, because that's how most people will really write it. And all this stuff out here just gives you the units of energy, and it contains the physical information, like the strength of the quadrupole coupling, and what the value of I is, R, and V also has units, so these units should be out there. So V second rank I, outer product I second rank. V is properly written in the principal axis coordinate frame. I is properly written in the lab frame. And the product of the nuclear quadrupole parameter times the elementary charge is the nuclear electric quadrupole moment. And that's usually what's tabulated. Okay. So that is our Hamiltonian. It's kind of elegant and small. I mean, compact in terms of the notation, but we can't use it that way, and we'll explain why in a second. So we usually talk about CQ, that's a shift in units of hertz. So like you would just read off of a spectrum. And that takes all the units out of that Hamiltonian and gives you something that's useful. It isn't necessarily the splitting you'll see in a particular spectrum. You're gonna have to worry about your Euler angles or whether it is motional averaging or whatever, but it gives you a sense of like how big it might be at 90 degrees. So EQ VZ Z over H in units of hertz, so not H bar because I don't want. Omega, I want nu in this case. So that's a kind of take-home parameter. You've just reported what the field gradient is along the extreme axis. Because the quadrupole moment, as I mentioned a bunch of times, is always the same number as the number you'll look up. So to know that is to know the question you were asking. Well, what is this field gradient? How big is it? And like if you had an octahedral or a spherical environment, I'm hoping for the number 0. I shouldn't have any gradient in it. And if I have a linear bonding environment, I should see something pretty big. And it should maybe help me if I compare it to, let's say, model compounds or ab initio calculations. It should help me learn something about bonding. Some numbers here because we talk about deuterium in this case. D2O, it's about 230 kilohertz. CD, we see a lot in the literature, and it's generally aliphatic, 167. Should say kilohertz. And for OD and ND is a typical number here. Strong dependence on whether it's hydrogen bonded though. And there are papers about that, like how that dependence looks. Okay, so here's the problem. It all sounded good up to this point, but the quadrupole Hamiltonian does not commute with the Zeeman Hamiltonian. And you know that this always creates a problem in real life and a poor assumption in the class. Like both always result from realizing that, right? So the quadrupole Hamiltonian, it will have all the spatial directions in those two copies of I, right? It'll be IX, IY, and IZ. And the EAS of the molecule that you would use to describe the field gradient, V, it is not necessarily going to be parallel to B or anything like that. It'll be like however you place the molecule in the div. So if I expand that out using spherical or Cartesian, either one, I'm going to have all the geometric complexity, spherical harmonics. I'm going to see a lot of raising operators, lowering operators, like the dipole coupling. But unlike the dipole coupling, it gets quite large in some cases. So dipole coupling, we talk about a really big dipole coupling being like 50 kilohertz, right? Yeah, that's big. That's like, takes over your spectrum. But how big do you think like a really big quadrupole coupling? Right. I mean, I just said that I thought deuterium was small, and then it turned out to be 200 kilohertz, like bigger than any dipole coupling, right? All right. So what happens when the coupling is that strong is related a little bit to your last question, Zardy, which is that the quantization axis for the total Hamiltonian isn't dominated by Zeeman. So if you ask a molecule, just place it randomly in a midfield instrument. If it has a decent sized quadrupole, like 4 megahertz or something, and you ask it where Z is, it'll say, oh, I think it's over there. You know, it's like a broken compass or something, right? And then it'll be around Z because it's not 60 megahertz coupling, it's a 4 megahertz coupling. But this leads to significant inaccuracy if you blow that off. The fact that the net quantization axis is not Z, and this is what we refer to as the high field limit. The high field limit is no good for almost any EPR experiment. It's rare to find an EPR experiment where it's okay, and it's not okay for the majority of quadrupole experiments. You can just put a circle around the ones where it's fine, and then you can play around with an approximate Hamiltonian where you pretend that the quantization axes never move. Because if you do move them, if you do move the axes, then that whole expression there is not a second rank tensor. Not necessarily. It could have terms that are 0th or 2nd or 4th rank. We're always strictly 2nd rank when we make the high field approximation, and we say that I is I along Z, you know? So a lot of things go away when we say it's not second rank anymore. A lot of our toys don't work anymore. So let's first just think about a case with a small quadrupole. And it's not just deuterium, there are lithium, there are a few other examples of quadrupoles that people like to study that are reasonably common and also have quadrupole coupling strengths that are less than about a half a megahertz. But deuterium is the one that you see most often in physics. So then you can make a first order Hamiltonian to make an approximation. And what you want out of that thing is that it commutes with the Zeeman. That would be wonderful if it has something that's made entirely out of the diagonal elements from our spin operators. And that is the first order term. Now you can make that from perturbation theory, or you can make it from the theory we went over about a month ago, it's the average Hamiltonian theory. So you have a complex Hamiltonian and you want to move to another frame and then average it. So the frame you would pick is rotating around Zeeman and just see how much of it is preserved if you average around the Zeeman. You get the same answer if you approach it those two ways. You get something that's traceless, second rank, perfectly follows the second Legendre polynomial, and it's going to behave just like CSA or dipolar, especially like with respect to magic angle spinning, which is terrific. And this is the expression. So for this, I want to emphasize that what kind of operator you're left with. You know, in terms of talking about it commuting with the Zeeman. And then I gained everything else together into one prefactor with units of angular frequency. So strictly speaking, if you wanted an energy, you have to put your h bar back in. Or if you want a frequency nu, you have to divide by 2 pi. Now, what is omega q? I give two expressions here. This is the one that we would be thinking about if it's uniaxial, and it refers to CQ, which was already defined on another slide. It's a product of the nuclear quadrupole moment and the field gradient, and then the spin number. And this is just P2 cos theta for a uniaxial case. This expression down here, without any geometry and just this overbar, refers to if you had something like a liquid crystal. All right, so it's not going to be time dependent. There's no magic angle spinning involved. It's just, it's averaged its value along Z over time. It's a time average. Okay, but that's the kind of Hamiltonian that you would have if you can make that high field and first order approximation. Now, what about the rest of it? Most of the cases that are quadrupolar are not small enough to make that a useful approximation. So for typical and strong quadrupole couplings, the same approach, perturbation treatment or average Hamiltonian, will give you something with these kind of terms. Those are for the spatial field gradient degrees of freedom. You can think of those as outer products. They're not second rank. You're generating objects with 4 spatial indices, not just 2 objects that depend on the 4th Legendre polynomial, not just P2 cos theta. Either approach, whether you do perturbation theory or whether you saw this when we did the average Hamiltonian, that you get a formal factor of 1 over the main interaction out in front. And then the next term in the series, which is sometimes discussed in this literature, you can see papers on the third order Hamiltonian for really strong quadruples. You can see papers, people thinking about that. But for that term, you expect now 1 over omega L squared, right? So this is a series that will become small if the quadrupole coupling is actually small compared to the Larmor frequency. It will converge nicely. But this is good to point out that the strength of this term, this prefactor, can be thought of as 1 over omega L, because it means if you go to a stronger field, you can make it smaller. Or if you do a field dependence, you can manipulate the size of it, and that helps you fit your data. Yeah, but these are pretty complicated. These are geometrically a different beast than what we've been dealing with up till now. Now, I just want to briefly look at a couple of spectra. You remember I was saying that when we were looking at the coherences, the density matrix, that we could talk about subspectra. That the m equals 0 to m equals 1 levels could be thought as 1 level pair. Not that you're going to take it out of that matrix for calculations, but just to think about transitions. And that could correspond to one of the transitions that you'll excite, characterize, and then the other level pair. And if you just had the Zeeman interaction, they will be degenerate, right? I mean, it's always the same frequency. If you add chemical shielding term, it shifts the outer levels in opposite directions. It goes like an IZ type operator. It's not drawn here, but I can do it with my hands. You'll just widen them or bring them down. It's not going to relieve that degeneracy. Okay. But if you add a quadrupole coupling, it will affect the outer states similarly to each other. It's actually an even function of m, and that's what's drawn here. So you raise both of them, for example. And it will affect the middle level differently. The energy of the levels is affected in a qualitatively different way by the quadrupole coupling versus the chemical shielding. And therefore, the quadrupole coupling does remove this degeneracy, and you get 2 lines. You can see those 2 subspectra right there in spectrum. And the 2 lines will be shifted relative to the Zeeman by equal and opposite amounts. Again, because this line comes down in this example, and these 2 go up. Now, this is exaggerated. If you really had a quadrupole that was that strong compared to the Zeeman, good luck. It's going to be a small little shift, but it's just drawn that way so you can see. Okay, so the 2 transitions might be, you know, this line and this line. Think of it as those 2. Plus transition and a minus transition. Any questions about that?
I'm just wondering, like, how much, so this is a span of like 100-ish kilohertz in this particular case.
Right, that's actually realistic numbers for a static deuteron, yeah, and a CD one.
Right, and how much chemical dispersion does deuterium see? Is it possible to do?
It's very, very similar to proton. The isotope effect is small. You can see it in solution in but it's pretty small. So 10 ppm, and let's say that would be a 60 megahertz on a 400. So 10 ppm would be 600 hertz. That's a big shift, right? That's like you're going to an acid from an aliphatic or something.
Yeah.
So you don't see this. The only time that I'm aware of where you see shielding, we did a lot of work with deuterium measurements in paramagnetic solids. And fitting the line shapes, model compounds. That is a shielding interaction formally. Due to electrons, changing the local field, follows the same mathematics. You should do ab initio calculations to understand, you know, like you can just, the analogy is more or less perfect. And as a Hamiltonian, it will behave the same way also. Because those electron states are not quantized on our time scale, they're just classical like shielding contribution. So anyway, that's big. It can be as big as the quadrupole interaction, comparable. So then you break the symmetry in interesting ways. And if you get a really narrow line on one transition and a broad one on the other, like a TROSY, yeah, they're kind of cool. But normal shielding diamagnetic, it's just like, people don't even include it in a fit normally.
So with 100 kilohertz plus magnetic of spinning, you get chemical shift resolution computing. And spinning much faster than 50.
I'll go back and finish those other slides in a second, but
Right.
you're gonna have, I mean, these are old spectra, but I always like to show these because Bob Gold was doing beautiful work with NAS deuterium early on, and it's an interesting paper where he was asking everything, but you could probably find better examples now that they're fast spinning. You're gonna get, 100 kilohertz, you're gonna get. Nowadays, you could get just a few spinning sidebands. Here he was spinning at 2 or 3 kilohertz in order to be able to get some subtle indications of motion. That's what he's after. A lot of deuterium solid state NMRs, its goal is not so much structure as motion. Yeah, it works really well. It works well over a broad range of spinning frequencies. That's what you're asking, right?
Yeah.
Okay, let's go back. And then I was just saying what you could probably figure out just visually. You're gonna have a pink pattern. You have a histogram of orientations on each of those two transitions, and they present in a spherical, they say Batman-like line shape. Sometimes instead of reporting CQ, people report the splitting between these so-called horns. Because if you have not very good signal to noise, that's the mean projected out restraint, those two pieces. So the difference between them is sometimes the frequency that's reported, and then you have a factor of 3/4, and you have to just let the details. So the splitting for CD bond is about 125, while the fundamental constant is 167. And commonly, you'll also see metal groups, and those are rotationally averaged. And the geometry is such that you get exactly 1/3 of those numbers. Okay, so you see Pake splitting. So I just wanted to make a comment here, and maybe this is something we can come back to more later, so I'll be brief now. But even for these small quadrupole deuterium, it's demanding in terms of the spectral bandwidth. It sets a challenge. When you want to pick up with some degree of fidelity a signal that spans, 100 to 200 kilohertz. One of the things is that you'd like a short excitation time, like if possible, south of 2 microseconds. And that's because your excitation itself will have a pattern, a sync pattern as you go off resonance from wherever you delivered the pulse. And you're going to have crossings, zero crossings at 1/500 kilohertz, zero crossings in the excitation profile. You don't want that because that's kind of crowding, coming close to where your spectrum is. You obviously want to digitize out to a megahertz or so, and that's not a problem with modern spectrometers. It used to be somewhat challenging. But to deliver a pulse that short, you need high power amplifier, and that's plain and linear and everything. And then you also need a probe that handles those kind of powers. For a short pulse, that isn't necessarily that much of a challenge, but it is a requirement. And then if the probe has a Q that's considered good, like a high Q means good signal to noise. Like in EPR, they like to have Qs that are 10,000, but our probes typically are lower than that. They might be 200 or less. But if it's a higher end, that will also impose alteration of signals in the wings. And so you don't want that, or you have to include that fact in your simulation. And the probe tuning must be symmetric. You need to check that if you place a signal on the right edge of the spectrum, you don't get a very, very different thing than if you place it symmetrically on the left edge. The probe characteristics for some probes are very symmetric, for others are not. So whatever artifacts you're getting on the edges, you might want to actually characterize them. But the main thing is that for these kind of broad line spectra, especially for deuterium, we consider detecting with the echo as essential. So the first few data points are crucial to getting the line shape. You could write out some data points at the end of the FID with no problem, but those first few data points are really important. They are going to determine the overall shape of the line, and they will be polluted with ring down and receiver dead time if you try to pick them up right after your pulse. So that's a hopeless thing. Okay, so then these are just simulated spectra that show the effect of various motion models on a static deuteron like this, as you start to have different kinds of characteristic motions of CD groups, like a 3-site hop of a methyl or a ring flip or trans-gauche and a long aliphatic. You get these characteristic line shapes. And you also see contributions, if the motions are fast enough, to spin lattice relaxation, and those contributions can be crystallite dependent. So this is just a really popular probe of dynamics. Like I think solid state NMR dynamics, I'm pretty sure if somebody did a count, you have more deuterium papers than anything else still today. And lots of really clever things that we don't have time to talk about today. Now, I want to mention, yeah.
Sequence, is this the normal harmonic or?
That's the next topic. That's the third time you guys did that to me. Can you just wait till I open it up? That's like the last thing I'm going to say about spin one. But before I say that, I was simply going to say, be aware. There is a field of making measurements without any applied field. Nuclear quadrupole resonance, in absence of the Zeeman interaction, just the quadrupole Hamiltonian, nothing else. RF-induced transitions between sublevels. And this has practical uses maybe we can talk about it more later. But it's a whole nother aspect of quadrupolar nuclei. And this already was said in answer to your questions, Anish, but for solution NMR, the rapid isotropic rotation renders the coupling 0 for these moderate size or small quadrupoles. And it also induces typically quite a lot of relaxation. And as a result, you can have broad or missing lines. And if the quadrupole is something that's attached to you, you can not have any scalar coupling that you can see, but that doesn't mean it hasn't perturbed the system in terms of its relaxation properties. Now, your question. Equilibrium magnetization. If I want to actually make any use of this apparatus that we developed, equilibrium magnetization is proportional to IZ, as you might expect. And if the Boltzmann factor is a ratio of the energy to KT, then that equilibrium magnetization is that Boltzmann factor P over 3 times IZ. Excitation pulses will be represented as rotations. They have to be applied bilinearly. So this would be the calculation representing what do I get after a 90? Start with my equilibrium magnetization, which is this, should have been P over 3 out here, I forgot it. Okay. And then I apply my rotation twice. So the first one would be R around X by pi over 2, and the last one would be R around X by minus pi over 2. So that's a bilinear application of my X pulse. And then I have to do that calculation to get a resultant, and I can re-express the resultant as IZ cos theta minus IY sin theta. So that's the effect of your initial pulse. We're building up to the echo that you asked for. But I have a question already about what I did there. It gave the expected result. I start with IZ, I give an X pulse, and I ended up with minus IY after 90 degrees. But notice that we didn't have any quadrupole coupling during the pulse. Right? I just had the pulse. I turned the couplings off. You've been doing that for all your solution NMR experiments. is that okay? You know, we can't be on resonance for both of the lines. We gotta be in the middle. So we're off resonance and there is a quadrupole coupling. And it's not true that the RF field is much, much bigger than the quadrupole coupling either. That's another reason you like short pulses. So that you have some justification for ignoring the quadrupole evolution during the pulse. It's not a great approximation here, but it's always made for deuterium spectroscopy. I don't really think about that conventionally. It's probably some small correction should be applied. I got another question for you about how we're doing this. So I did it in a way that was brute force. I said, here's my density matrix, here's my rotation, let's just calculate. But what else could you do? Something else that we did in this class that you could have answered the effect of the 90x pulse on equilibrium magnetization. What else would you like to do that?
We could also.
Yes, thank you. Take some commutators. That would have been the clever way to do it. And if you do want to grind through, do consider like getting some help. You can do smaller calculations with the free version of Mathematica, like alpha, Wolfram alpha or whatever. It's pretty limited. Or you can ask somebody to pay for real Mathematica, or you could use MATLAB or something, but it's pretty tedious to do it by hand. Now, here's something you could do at home. Saradi, about your own question. What if you assume after you're done with that first pulse that mostly it's just got a chemical shift? Let that evolve, hit it with a 180, let that evolve, and see if you form an echo. Okay? And you can do that with those commutators. It won't take you very long. Don't do it the hard way. But keep in mind that this is just an exercise because I can't give you an example of a spin 1 where the CSA is bigger than the quadrupole. It's not very physical, but it's a nice little calculation that you could do. And it works. The echo will work if you do that. But let's do something that's actually a good model for solid state deuterium spectroscopy. So this is free per session. We're only going to use the first order Hamiltonian. We're going to throw away the rest of it. We're not going to have interactions during pulses. So we're making all the convenient assumptions. So Zeeman is much bigger than the quadrupole, which is much bigger than everything else. And I should have said that the RF is bigger than the quadrupole. I should have had one more thing in this chain. So it's I equals 1 spin. It's in the rotating frame. We're assuming that at least the chemical shift is on resonance. And we're assuming that somebody already hit it with the X pulse. So we're beginning with minus P over 3 IY. That's where we start this. So we develop an echo sequence. Now, one thing we need is a propagator for our quadrupole Hamiltonian, because our assumption is that we don't need any of these Hamiltonians, we just need the quadrupole. So we need a propagator for it. And that would be to exponentiate this matrix. And when you do that, you get that. So if you evolve this, you get an answer, and that answer turns out to be conveniently re-expressed in this way. You have minus IY, and then later on it evolves and you get QX, that funny coherence that we kind of invented by hand. That's what you get if you let IY sit in the XY plane under the influence of the first order quadrupole Hamiltonian. You make that. And you can see that, you know, at time 0, you get the right answer. You still just in minus IY. So it seems like a sensible answer. And I did that by grinding through, but you could check it by doing the commutators by Baker's-Hausdorff, okay? So you evolve to form that. And let's say that you waited for a perfect amount of time. So you just had a pure quadrupole coherence. I'm just reminding you that you won't see anything in your receiver, right? This thing is not detectable. It's like antiphase magnetization. You have sort of 2 subspectra in there canceling each other in terms of net magnetism. So then you get a bright idea, what you asked me, can I just refocus it? And then I'll detect it when it becomes IY again. So I'm going to hit it with a 90. I'm going to make this out of it. And then I'm going to hit it with a 180Y. The logic being It won't affect this. But it should turn this upside down, right? Because that's an X-type coherence. That sound good? All right, so let's try it. It turns out that if I take IQX and I rotate it around Y, we made those rotation matrices, and I just grind through this, I get IQ back. It's not what we wanted. But it's not that it doesn't change it. It actually flips it around like a full 2 pi rotation. Because, and you can see that because you just do a shorter pulse. Like let's do a pulse that's only 90 degrees. It flips the sign of the quadrupolar coherence. So you start with IQX and you end up with minus IQX. So as a formal effect of the higher spin, that these coherences rotate under the influence of RF pulses at a higher speed. So that, therefore, the pulse sequence is 90, 90, 90x tau, 90y tau detect. That is quad echo, quadrupolar echo. There's an analogy in dipolar couplings, strong dipolar couplings of like spins. When you have the full dipole Hamiltonian, that you refocus those by a 90-90, not a 90. But we didn't talk about that yet this term, right? So that allows all these advantages we already mentioned for the echo. So you can do the echo, but you have to do a funny echo. So just to recap, for integer spins, all transitions are broadened to first order. That's a lot of broadening. For small quadrupole couplings, peak patterns can be observed in static solids. Ideally should be refocused with a quad echo, optimized hardware, and short pulses. For small couplings, MAS also can be used to narrow the lines. And for large couplings, too broad to detect by conventional methods, active area for development, N14. I didn't really develop anything on some of the new papers on N14. I didn't really think about that. You're entirely thinking about half integers, right? Yeah, and this could be something that we could talk about. N14 is like, it's kind of holy grail. It would be important doing it.
Snipe hunting. That's what some people call it.
It's snipe hunting. As in there aren't any. Okay, this is going to be really brief because I think the sooner we switch this to Eric, the better, because he has some very nice practical applications. But let me just say, having seen the development for I=1, I really think you could, if you wanted to, systematically develop this collection of coherences or populations, span the space for S=3 halves. This is a 4-level system, right? So you can find all the populations, you can find all the single quantum coherences. You're going to have some extra things compared to I=1. If you want to look at this, like in the problem session after you're done with your exam, we can do this a little bit more formally. But it's not going to be okay to ignore the second order Hamiltonian, and that will be important for, I'm sure, for many of the examples that Eric will show. So the central transition is special because this is the only transition between 1/2 and -1/2 that isn't affected by the first order term. So it will be affected by the second order term, but it's not affected by the first order term. Again, because of it being an even function in M. So whatever happens to the top level in that central transition will also happen to the bottom level. But the second order quadrupole interaction is not even in M. It's not a simple function. And we also said earlier that at high field, the second order effects are reduced. So the idea in the vision might be, why don't we measure those central transitions at very high field? That would come directly out of what we said before. Maybe just I'll leave this for Eric to talk about. I'll just say it is not okay to ignore the effect of such strong quadrupole couplings during the pulse. So I said we were going to do that for the deuteron, and it wasn't necessarily even a good idea there. But for the stronger quadrupoles, it doesn't predict lots of things that are important to see. So just rounding up, some kind of basic observations. For that half integer spin, the central transition is not affected by first order and therefore would be interesting to observe with MAS. But for larger quadrupoles, the spectral interpretation could be complicated by the second order Hamiltonian, which results in a lot of broadening and even shifting. And let me just leave the rest of it off, because I think these are things that you're going to illustrate very nicely. You can't necessarily cover the satellite transitions, the other transitions, or a large quadrupole. And so you end up selectively exciting the center band, and this has interesting implications. The larger picture that I would try to emphasize just at the end, it's not just that we want to cover the whole periodic table, but that quadrupole interaction is really going to deliver some interesting information along the lines of the questions you were asking before. It's going to provide an independent probe of local bonding, independent of shielding, and spectral simulation to obtain that field gradient, and then comparison to models like from quantum mechanical prediction could give you insights that add on to anything you learn from chemical shielding. Could be very interesting. Unveiling like symmetry or bonding environment or those kinds of things. So a whole nother world of molecular parameters that are out there to explore. So I also listed some readings. There's some really like beginner kind of stuff to parallel, like we were just developing what are the coherences and so on and so forth. And you can see discussions of things like that in a very nice book from Melinda Dewar. From the textbook we've used before, there's a little bit, but it's sort of oddly peppered through the book. There isn't just like a section on this. And there's a little section in Malcolm Levitt's introductory book on this. But I would comment that some of the conventions that he chooses are a little different than the other readings here. So you have to just pay attention to the details. In terms of like formal development and getting expressions for the spherical harmonics and so on, I would strongly recommend something that's from the 70s. It's an old book, but it's from Hans Spies called Rotational Molecules and Nuclear Spins. Just getting all these Euler angles and spherical tensor components and everything explicitly. And then some more advanced topics that touch on some of the things we talked about. Maybe particularly this one from Lex Vega. So I was going to stop at that point. I kind of skipped a few things, but that's okay because I know we're going to catch those topics. Now, you guys have normally a homework session.
Yeah.
Yeah. How would you feel about taking a little break and then talking a little bit after the break? Would you like that? And then we'll have plenty of time tomorrow also. Sound okay?
Yeah.
This is like the Wednesday marathon. Young Jin, you doing okay? You still there?
Yes, I'm here.
Hi. I didn't check the chat. I'm so sorry. If you were trying to ask something, I'm really sorry.
There's no chat.
Okay.
There's nothing on the chat.
Okay.
Thank you.
So we're going to take a little bit of a break, and then we're going to switch speakers just for a little bit for today, and a similar topic, okay? Now, we have a host for the Zoom, so I can just get off of this.
Okay. Yeah.
Do you have the link? First, stop my share. Then I'm going to leave it. Then I'm going to email you. Of this. And I have. Here's some birds for you. Do you want to use this power?
Oh.
I just don't want to forget it and leave it, but I'll leave it here for you for right now. And this is the NYSBC. It hooks up with the USB
Oh, okay.
or the
For the
display.
Display. and
Yeah.
everything.
Remember how to do all this stuff. I didn't really use this. This is my laser pointer if you want to have access. Oh,
I think I'll need it.
yeah, I don't think so either, but it's right here if you change your mind.
Very different way of doing this.
But no. Shoot, great job. Great job. Nice work. Nice work. Did you have any technical difficulties with the coursework? Okay, good. Well, some people did, and so I was like getting these emails in the middle of the night on Saturday, and I was asleep, and so I was able to like, why are you taking my exam? No, go to bed. I want to go to bed. Stop it.
I heard. Cyrus,
Yeah.
Yeah.
No, he was very, very polite. Cyrus is always very polite. But then somebody else had an opposite problem, like they found more than one copy, but it was identical. I'm like, okay, so calm down and take it and turn it in. It's something I had done for Cyrus in case my first idea of how to fix it didn't work. So I had them like all over coursework. And I'm like, well, if they want to cheat, enjoy, because it's right there in coursework. So.
How do you want us to turn in this system?
Oh, Art didn't say anything, right?
But it's easy by it to work.
Sure. Yeah, I think you can turn it in any way you.
Okay.
Now, the only thing that's nice about sending us the photos is that then we don't have to. I can look at it and let Art have it also.
Okay, yeah, that's probably better.
So that I feel like it's not getting graded, I can just.
Yeah,
Or if I just want to grade this all as they want.
yeah, that's it. I do that.
But honestly, whatever you do is, this is small plus.
It will just be a long document.
Yes.
It will be a long document.
Yes. Now, I'm pretty sure all the problems are actually solvable in this class, not for biophysics, but in this class. There's been a history of like after a week, it's like there's no deadline for no deadline. And then after a week, one of the instructors will remain nameless. It's like, I don't think it's possible to solve my problem. But I'm working on it all. But I actually think you guys, your exam is fun. It's all possible.
There's a way out there.
And we also had a history of just continuing on teaching all the way through the summer.
What?
Well, if you like waterfalls, a lot to talk about here. So do you still see one or two people on the Zoom? Can you see them? Ron, Jen, maybe the only one?
Yeah, I think so.
Okay.
Can everybody hear me can you hear me, Jen? Or,
Yes, I can
Okay.
hear you.
okay, great. Wonderful.
Well, thank you. I think Eric is going to introduce himself. And I think actually you all maybe met him also, but I said it as at the beginning, we're super lucky to have you join in the class because I talk about quadrupoles. We haven't done deuterium in a long time, and it's the only single quadrupole I ever really did much of anything with. And there's the whole of the periodic table, but Eric, as he'll show you, has some quite remarkable experience doing cases that I think come ever closer to biophysical applications and are really super interesting. So, and you probably know him as the solid state research. I'm giving you the wrong title. Research. Solid state spectroscopist, research scientist here at NYSBC. So if you learned something today that's interesting, and interact with them. So thank you so much, Eric.
Yeah, well, of course, thanks for having me. Yeah, so I'm gonna talk a little bit about like this, maybe, but it's not.
Yeah.
Sorry, can't see my mouse, so. I do a piece that so that it's more hidden. Back into that, okay. Okay, so as Ann said, I'm the staff scientist here for specializing in solid state NMR at NYSBC. So obviously any solid state NMR needs, I'm here to help with that, particularly if you're running experiments here at NYSBC. I've been here since 2021. I started out in solid state NMR many years ago in the group of Philip Grandinetti at Ohio State. I started in 2009, working mostly in looking at measuring CSAs in silicate glasses using some really interesting physical hardware techniques. Experiment called magic angle flipping, where the spin angle of your rotor is actually changed in the middle of your experiment to help correlate different interactions, isotropic and anisotropic. I moved from there, I moved to MIT to work with Bob Griffin, where I worked on oxygen 17 NMR. And as Ann said, oxygen 17 is a half spin, half integer quadrupolar nuclei. A lot of times you'll hear that terminology for things that aren't deuterium or N14 lithium 6, right? That's the spin 1. That are spin 1. There's also larger spin integer quadrupoles that are spin 2, spin 3, spin 4, but they're not really done for various reasons, in that you need a small quadrupole if you're integer spin, whereas we luck out in some ways with spin half integers, which we'll talk about. So I did that working on development of oxygen 17 for use in peptide and protein samples moving forward, as Ann said, something that approximates biological relevance. And then I moved to Columbia and worked in the group of Ann McDermott here, working on something completely different in measuring millisecond to microsecond motions in proteins that didn't touch on quadrupoles at all. If you ever happen to run into my undergraduate advisor, Philip Grandinetti, you'll find out that he does a lot of work in quadrupolar NMR. I did not do any of that in my undergraduate. I kind of took a weird route into it by moving on from a renowned expert in it to somebody else who also is very good in that field, but wasn't sort of the way you would think that built in my career. So just to kind of reiterate the quadrupole interaction, and Ann did a good job of talking about why do we care? Well, it's most of the periodic table that have spin active nuclei. They have a quadrupolar interaction. This is just the same Hamiltonian that Ann showed. It's, notation might be just slightly different. I put the H bar instead of 2 pi and H. We have, IVI, where you have this EFG tensor that we're going to describe using, 2 parameters. One to describe sort of the magnitude of it, the quadrupolar coupling constant, or CQ, you'll see, or nuclear quadrupolar coupling constant sometimes, and an asymmetry parameter that describes sort of the shape, whether you have that sort of prolate or oblate, the frisbee or, football, shaped tensor in space, where in sort of the field, where you have a magnetic dipole here, you're processing, you put it in a magnetic field and, your nucleus processes around, this external magnetic field with the electric quadrupole moment, this Q II here. We're going to put it in an electric field and it's going to do the same thing. It's going to process around. And that electric field, as Anne had iterated, is just the electrons in the nucleus. So the nucleus is surrounded by an electric field. It's going to move in that field. If it has a gradient to it, so if it's non-spherical in shape, you're going to get this sort of EFG moment. You're going to get an interaction that's anisotropic in nature due to the anisotropy inherent in that. So what does this look like? So for, Anne showed, spin 3½ here, spin 5½ I'm just doing that because I'm going to talk a lot about oxygen 17, which is the spin 5½.
I was scared of that, so I didn't put it.
Yeah, it just has more transitions. So you have your central transition here. As Anne said, that's the only one that is unaffected by first order quadrupole interaction. You move to second order and you can see that it is affected in that case. All of these transitions that you see here are unaffected by that zero order. So going M plus to minus, you're symmetric about that. They're all unaffected by that first order quadrupole interaction. This is where you end up in the instance of the spin 5½. You have all these different transitions. Sort of these ones are described in general as satellites. So you have satellite transitions, and then you have your central transition. Which I could write better on this, my iPad and my pen, but
No, it's legible, it's nice. So you're pointing out that the multiple quantum ones are also, if they're
yes.
like X to
Yeah,
minus X.
from if you go from sort of M initial,
Yeah.
M final, and that goes like from -1/2 to +1/2 central transition, that is unaffected. -3/2 to +3/2 unaffected. -5/2 to +5/2 that's unaffected. So I'll talk a little bit more about that in a later slide. So what I'm just going to talk a little bit about here is just a little bit of a different formalism for looking at this. It's going to be important with the way I build up and how I think about these experiments in some of the ways. So I just wanted to introduce it. So you have a transition between two states, I and J. You can describe the frequency of that transition, the NMR splitting, using the sum of multiple different components. Each of those multiple components of the frequency can be broken down into the product of three different things. One is just a strength component, so that doesn't have any other dependencies. One is spatial, and then one is the spin terms that we like to think about a lot about. The spatial terms are always there in those spin terms that you've been looking at. There's nothing new here. It's not anything different. It's just a different way to write the same sort of equations. So then if we take this sort of formulism, and we talk a little bit more about it, let's just talk about the spatial component because that's going to be important. The spatial functions are proportional to tensors of rank L, so spatial rank L to a tensor of rank L. In this case, the spatial symmetry of these functions is then determined by the spatial symmetry of that, tensor that it's proportional to. And then we generally, the way we express this is using L rank Legendre polynomials. So you have Legendre polynomials. I didn't break out the equations for each one, but they each have a rank L where they have a root or a solution. For rank 1, that's 90 degrees. That's this blue linear line. For a rank 2, this is where the magic angle pops out, we're all happy, we have an angle, we have this red line here in the center, with one single intercept that tells us, well, if we spin at that angle, we can effectively eliminate these spatial symmetries that have rank 2. In the case of rank 3, you get the green line. In the case of rank 4, which is what is going to be important, you get this second line here. And one of the important things I want to note is, while there's 2 solutions to this Legendre polynomial, they don't intersect 0 where the other one does. So that's going to create somewhat of a problem for us, and an opportunity in the same way. So what does this mean? Well, if we break out sort of the contributions in frequency for a quadrupole nucleus, we have, first off, the first order nuclear shielding. That isn't anything unique to a quadrupole. Spin half has that. It looks exactly the same as it does in a spin half. You have, I've broken it into 2 parts. You have 2 different spatial symmetries here, S and D functions. You can think of these kind of the same way you would orbitals, like an S orbital, D orbital. So this is going to be the isotropic component. It's got S symmetry, so there's no way to get rid of that spatially. It's like a sphere. There's nothing you can think about to do. This one has D symmetry spatially, so that's something that we can think about, a way to eliminate spatially. You have your first order quadrupole, same thing, and here you have this sort of spin transition diagram. That's like the transitions that you're going up and down. This we can eliminate in the clever way of only doing M, I, M, J symmetrically. So, i.e., we're only going to excite transitions that are from 1/2 to -1/2 or 3/2 to -3/2, and we eliminate the first order quadrupole interaction. Now you can see you can't do that with deuterium because you have no even symmetric transitions, because you only have 3 levels. So you can't eliminate that first order in that way, which is why you end up with a broad line. As you can see, I've said this is somewhat on the order of kilohertz in anisotropy. This is on the order of megahertz. Obviously, with deuterons, it's smaller than a megahertz, but that's just kind of the luck of our luck that we can look at them. If it had a larger quadrupole interaction, then it would be much more difficult. And then, as Anne said, we can't ignore second order effects. So we're going to do second order quadrupole on the order of kilohertz to megahertz, and it has 3 different components that have 3 different spatial symmetries and 3 different spin transition symmetries. But another important thing to note here is we have in the front, the strength has a term in the bottom of it that scales as 1 over the external magnetic field. So this is saying, well, that's something. We just increase the magnetic field, we can make this smaller and smaller and smaller. Obviously, as you know, with the nuclear shielding, you have the opposite effect. It gets bigger and bigger and bigger as we get larger. So you can imagine the case of a lot of quadrupolar nuclei where you have this kind of terrifying middle ground where you're not quite high enough to eliminate much of the second order quadrupole interaction, but now you've introduced a significant amount of chemical shift into your spectrum as well. So you end up in this sort of worst case scenario, which is almost where we live most of the time.
Can I just ask you something
Yeah.
about this notation? So in the first order Hamiltonian, the spin degrees of freedom with that lowercase d is
Yeah.
referring to the symmetric transitions only. And for the,
It's actually not just the symmetric transitions. I'm saying we're going to select ourselves to only look at symmetric transitions. But the D, so in this, so this is from a paper from Philip Grandinetti, so I learned a lot of NMR from this notation. It's a paper in progress in NMR spectroscopy that's called symmetry pathways. And if you open it up, what you'll see is what this D sort of thing looks like, and this is not correct, so don't, but what it'll be described as looking like is something that looks like this. So just bear with me as I draw one of these. Try to. Okay, so then like on here you'd have MI and then you have MJ
Mhm,
transitions, and these are nodes.
mhm.
And then at each one of these points is basically a number. And these points here that go straight up and down
Yeah.
from the middle, those are the symmetric ones. And in the D case, they're all zero.
Okay.
But these numbers aren't necessarily zero. Some will be like +3. This might be, 27.
Mhm.
And so the way that you move about these sort of as your pulse sequence developing is that you can choose transitions. Say I want to excite with a pulse between, MI -5/2 and MJ +1/2. I can find that on the diagram and say, here on this D, if I draw it like this, then I'll have you guys discussed coherence pathway diagrams at all? Okay.
For like a couple spins, one half.
Yeah, no. So you have you look at it as a, coherence transfer diagram where these numbers would be, what I put here, one's 3, one's 27, then you have like a -3, a -27. So you've selected one of them from this pulse where we're going from here to there. And then if you spend enough time here in each state, you can create echoes in space if you equal the time that the coherence is such that they cancel each other. So obviously between 3 and 27, you wouldn't actually get this. This is just an example. It's not, as I said, not correct, but that's sort of how it looks like. So in the case of this D, there's nothing unique about this, the way this notation is that cancels it out. It's just, we're going to say, we're only going to select the central transition. We can eliminate that. We don't even have to think about the first order, even in spatial symmetry. We don't have to think about how well that averages with MAS anymore because we've already gotten rid of it because we're only exciting that central transition. That's no longer the case here at the second order. We can't just eliminate that. These C ones, which are a little different than the P and the Ds are pure. The C's are actually a linear combination of P's and D's. So it's a little bit complicated in that, but they just are the same sort of thing. It's just, one of these sort of diamonds with a bunch of numbers in them. You can look around them, but I'm not going to discuss too much. But yeah,
I actually have 3 questions.
that's absolutely fine.
My first question is, what is the coherence order of the detectable coherence? Like in half, we say minus, I minus is where we end up for detection.
Yeah, so essentially, you're only, this is where things get, you can only detect, you can choose, I guess is the best way to put it. You can choose to detect either P -1 or P +1. You can't detect both of them. You can detect one or the other. So it's still P -1.
Oh, okay.
So nothing's changing there, but this is basically saying other things are happening. But as Ann said, this, quadrupole, it's not, you can't detect it with your receiver, but it's still moving around. You can try to refocus it. So on this sort of, just to kind of, wish I had a blank sheet. I should have done that, but I'm just trying to think of where to try to write. So, sorry, brain is. So if you think about the sort of Hahn echo versus quad echo or solid echo pulse sequence, they both look exact. If you just think about them as pulse, tau pulse,
Yeah.
they're both the same. The lengths of those pulses and the phase of those pulses are different. But if you look at sort of on a P diagram, the where you have your three levels here. So you have 0, +1, -1. You hit this and you go up. And then you hit this and you go down. Here, let me just change colors so we can. You hit this, you move up, then you go down, and then when it's spent as much time in P+1 as P-1, you get an echo.
Yeah.
Okay, so the problem is that if you're trying to do D, what happens there, you have sort of your D pathway, and the other one, I'm just gonna switch. You end up with something that does this. You know, as I said, it doesn't do anything. You don't get an echo because you're not echoing out here, you're echoing in here before you actually hit it with the pulse. Well, right where you hit it with the pulse is where you echoed the D, so you don't actually get a D echo after that pulse. You don't fire the echo. In the solid echo or quad echo experiment, it's basically just the opposite. You're sitting here, you end up up here, and you end up back down at 0. You don't P echo, but you D echo. So you're echoing the D symmetry pathway and not the P. Now, there are fancy experiments where you can do both at the same time, but that's, you know, you're not just 2 pulses. You need more than 2 pulses. And you're not echoing them. Anyway, so, and I think somebody had mentioned something where where Anne was talking about PSA, paramagnetic shift anisotropy. So there are, you know, fancy experiments where you correlate quadrupole and paramagnetic shift anisotropy in deuterium NMR, where you have essentially a 2D where one axis is your quadrupolar frequency and the other axis is your shift anisotropy, and actually the shape in the middle of the spectrum tells you your Euler angles in between them. So I can show you, I mean, we can go into, these are experiments that were done in, you know, the groups of Simon Wimpress and Philip Granadetti has done some of it too, but you need a you need a case that has large enough PSA and quadrupole and small enough quadrupole that you can really do them both at the same time. So I think in the case of that, you're talking about some metal bounded waters. So it's a D2O that's bound to some metal that has paramagnetic. And then you can get these really, they're really cool looking spectra, just because you don't, there's a pretty unique sort of spectrum. So basically this is how that works. So I think you had more questions.
Yeah, I was just looking at that first term in the second order quadrupole is S symmetry, which means it's isotropic.
Yes. So we'll get there. So there's an isotropic portion to the second order quadrupole.
Can I see it in solution NMR?
Can you see what?
Can you see that second order quadrupole, the isotropic part of it? Can I see it in the solution NMR spectrum?
You will certainly see it in the solution NMR spectrum. Your shift will not necessarily be purely chemical shift. It will also have quadrupolar shift. They're just linear combinations. So the asymmetries, you can't separate them from each other. But in a solution NMR spectrum of a spin half integer quadrupole, your if you have a strong enough quadrupole coupling. Now, in most solutions, that's averaged pretty well to 0. So you know, the strength of the interaction, the omega q squared portion of it is basically eliminated in solutions. But we'll get to the point of that's an important thing to think about. So that'll come back up.
The last thing I was wondering was for spin 1,
Yeah.
the +1 and -1 levels sort of go up by the same amount.
Yes.
The quadrupole coupling, which means that the symmetric transition in deuterium is also first order quadrupole.
Right. But
That's an overtone.
that's the sort of multiple quantum
Double bond.
Yeah, this is done for N14 and a little bit
Yeah,
for
N14 overtone.
deuterium.
spectroscopy. It's nice.
But the kind of detection efficiency, the percent of the possible coherence that you actually end up detecting is a challenge.
I believe that, just like many other things, is a formally forbidden transition.
It
Yeah.
is.
Yeah.
So,
So you can do it at very low field. And I think sometimes they use what's called parallel mode instead of perpendicular mode, so you have different geometry. Or I don't know, maybe if we thought harder about the kind of excitation schemes that are used in the multiple quantum transitions, maybe there's another.
Yeah, I have to look.
But I know that there's no home run. I mean, there's not like you don't get 100% in sharp.
No. No, and then you're, with N14, you're fighting the fact that it is incredibly low gamma. I don't know what it is, but.
Well, somebody did it
But
in,
it's-
when I was in
it's very,
grad
very
school,
low.
somebody was measuring it for head groups of lipids, and I think it was possible only because they were almost liquids.
Yeah.
And yes, it was low. It was just a few megahertz
Yeah.
or something.
It's like a couple megahertz at like 400, so.
Yeah.
Yeah. So, hence why I say snipe hunting. Like, people try to do it because it's really interesting to try to do, but it's really hard. Okay. So right now I've just highlighted, we have two isotropic contributions. They contain S, as Anish pointed out. One is in the second order quadrupole, and one's just our regular chemical shift that we think about. And if we want to do high resolution NMR, we want to eliminate all of the things in red, all of these anisotropic contributions. So that's CSA, first order quad, and these two second order quadrupolar terms. How do we normally do that? We normally spin. We do MAS. This is, wonderful. We've exploited our spatial symmetries. We take our D pathway and we find its solution on the second order Legendre polynomial. We put our rotor at that angle and we spin rapidly about that. And this is just the root. This is actually, an expansion of these Legendre polynomials that, the stuff in green is what gives us spinning sidebands. So they're time dependent, whereas the other part isn't. So that's why you have these spinning sidebands. The faster you spin, the more they get eliminated because of, the omega RT dependence there. So as we shorten that. Okay, so we do that. We put it in our magnet and we spin. So we've eliminated now all of these anisotropic contributions here, but we have a problem. There's still residual anisotropy. We didn't eliminate this G spatial symmetry in our problem. So what are we going to see in our spectrum? If we put our half energy nuclei in there and we just do a block decay, we just hit it with a 90 pulse, or what we think is a 90 pulse, and we just acquire. What does it look like? We only have one resonance. We're not going to do anything else. One resonance
Under the NAS.
under MAS. What does it look like?
Powder pattern.
Or
Like a powder pattern? Okay. Yeah, so that's exactly what it's going to look like. It's going to have a powder pattern. You're going to have some residual anisotropy. Now, what's the great thing that it looks like? Okay, so problem. It's broad because it has a powder pattern. Powder patterns aren't incredibly narrow. They have some amount of shape. What's the advantage that we have that now? I don't like looking at everything as, negative. So what's the positive? We have a powder pattern. What's the positive?
Information.
Yeah, so there's structural information in the powder pattern, just like there is, in everything. So, as spectroscopists, we spend a lot of time trying to narrow our lines and then be really clever about trying to get back all the information we got rid of by narrowing our lines. So, so in the real world, what does this look like? If we're able to excite the entire breadth of the spectrum, all the transitions, we get something in a static spectrum that looks like this. This is, real world, what it looks like. If we zoom in, we have a central transition. This is just for spin 3 halves. We've gone down to 3 halves because we don't want those extra transitions to make things more complicated to us. We have this green, really what looks like a very narrow central transition. Then we have these satellite transitions, which are these broad patterns out here. There's 2 of them, opposite directions, just like a Pake pattern. The shape is a little bit different, but don't worry about that. That depends on what you put into this. If we zoom in on the frequency here, so you notice that this frequency axis is in megahertz. So, good luck exciting that pattern. So this is where good luck, and also good luck to us because we can't excite that whole pattern. If you zoom in, you can see just what the central transition looked like as Anisha, there's a pattern there. That's not just, and this is static. So you have a pattern static. We do the same thing where we spin. You get something that looks kind of like the deuterium spinning, except for here, we're not spinning at 2 kilohertz, but it wouldn't matter because we're still on the order of megahertz. And you end up with a powder pattern that looks like this. It's narrower than it was, but it's still broad. And why? Because we still have that residual anisotropy, residual second order quadrupolar broadening. You'll hear that term called. So, but there's structural information in this powder pattern. So what does this look like sort of in the real world? If we take a static spectrum of a carbon compound here, just, a ring carbons, and then we do MAS, we eliminate those residual CSAs and dipolar couplings. Maybe we're, deuterium, we're proton decoupling. Talk about here. We're proton decoupling, so we eliminate those as well. We do the same thing for something that's not spin 1/2. So we're spin 5/2 here. This is, FMOC protected amino acid, leucine, labeled with O17 on its carboxylic acid. Oxygens, you end up with a broad line. It's got residual alignment that's quadrupole, that's CSA, that's dipole couplings. In this case, we're decoupling protons in at the top spectrum and the bottom, and not in the bottom. We don't need to in the bottom spectrum actually. But we spin fast and we still get a residual line width that's fairly broad. We can see that we have 2 peaks. So, we've got chemical shift resolution, but only because these have a fairly strong shift in where their chemical shifts are at. You have a good dispersion. Talk a little bit about that. That's spinning at, 54.74. So you have this interaction here that's not being averaged. That's what gives rise to the line shapes here. So this is your second order quadrupolar broadening.
Question.
Yeah.
You can do a magic and the flipping experiment here also. Right?
Yeah, we'll talk. We'll talk about that. So we'll talk about other things. So let's just talk about the central transition, because as you saw, it's not so bad if we can just get the central transition. We eliminate the first order by it being symmetric M to minus M transition. How do we selectively excite this? It's actually not complicated. We just hit it with pulses. Our pulses are so weak that they're effectively selective no matter what we do. There's still technically some satellite transition that exists in the spectra, but it's excited at such a small and weak area that effectively, even with a hard pulse, we're selective. We don't need to use any special fancy shaped pulses or anything like that. We just hit it with hard pulses that are not effective at hitting megahertz transition. So once we have the central transition, now we can effectively think about the spectrum as a spin 1/2 nucleus in the way that we treat it spectroscopically with pulses. But obviously there's still second order quadrupolar interactions happening in there. So it's not, the spin stuff that's happening isn't quite, but we can think about it as a spin 1/2 nucleus. We can hit it with, pi/2 pulses and pi pulses, and, think about inverting things and all of that. We don't have to think about this. We need this massive, breadth of pulse width like we do with deuterium, where suddenly we're, I can't excite, 400 kilohertz. My spectrometer's too old and I can't do it. This obviously is not something that we think about too much now, but it is still a problem in some instances, particularly with probes. As Anne didn't really mention, but in practicality, most deuterium static spectroscopy is done on a probe that is tuned to a single nucleus for various reasons. One, you can have a probe that's much more robust to RF, so you can hit it with really hard pulses. You can also tune it so it's really well balanced and symmetric. All this stuff gets much more difficult. So a lot of static wide line deuterium NMR is done on a static X probe with a coil that's at 0 at 90 degrees. That's because you get better excitation with your coil there than your coil here. That's how the physics works for that. Okay, so what does this look like in space? So you can have different quadrupolar couplings. Here I'm looking at oxygen 17 at 750 megahertz, so it's about 100 megahertz mutation. Like that's the field of oxygen 17 at our 750. If we have sort of a 1 megahertz quadrupolar coupling, you can see that you can't really even see the shape. It's almost Gaussian line there, integrated intensity great. As we go down, this is sort of the real world. As we increase, the quadrupolar coupling, this gets broader, so our detection sensitivity goes down and down and down. So if we have something that's effectively symmetric, you have really good detection sensitivity, but when we're down here, we can't even really see that peak anymore. This is just blown up, so they're all at the same height. You see that the CQ going from 1 to 2.5 to 5 to 7 to 10, you get broader and broader and broader. The reason why this is all bumpy at the end is just I didn't simulate with enough crystal lights for that breadth. It's just a simulation artifact. So they're smooth when I'm well simulating it. I start to not simulate it so well, it gets this broad, and then you start to see the spinning side bands coming back in here of the simulation. You kind of see them here, a little bit there. You can't really see them here, so they've eliminated, that echoing of the rotational echoing of the G anisotropy. Yeah.
What is the range of CQ for 17?
The range of quadrupolar coupling for 017. It's fairly strongly dependent on what you have for your environment, but it obviously some things will be very, very, very small if they're perfectly symmetric. But usually right around 5 to 11 megahertz for most things.
What would you consider small for oxygen?
Small for oxygen? Yeah, in a lot of the oxygen materials like silicates and stuff, they're on 4 megahertz. That's fairly small.
So like a tetrahedral symmetry on.
Oh, that would be even smaller.
Yeah.
But because it's gonna fall close to 3 to 5 in sort of ideal
That
scenario.
also hold true for water.
For water.
Yeah.
In what case?
What's the coupling
For
constant?
for
for
liquid
oxygen?
water?
Well, if you froze it.
If you
Also-
froze it. Yeah, we'll talk about that.
Okay.
So you'll find out that a lot of my work is in water. So not in ice, but in bound waters. So then what does this look like if we look at the different shapes? So if we change the eta, which is defined here as just the difference between the XX and YY components of the EFG tensor divided by their magnitude. So just an asymmetry, you get sort of this very clear change, just like you would in sort of a static chemical shift spectrum. So then how do we exploit, and extract this information? Well, we fit the spectrum, just like you would anything else. So, but one note to that is that in the case of most spin half nuclei, your applied field, B1 field, is around or much smaller than the quadrupolar coupling. So if we're applying a 50 kilohertz field or 100 kilohertz field, in this case, it's showing this is showing a 50 kilohertz applied B1. If your CQ is 1 kilohertz, everything looks normal. As you start getting toward parity with the omega one, you see that these are no longer following what you would expect for a 50 kilohertz field, having a 180 at 10 microseconds and a 360 at 20 microseconds. 50 kilohertz we're now here, and here for those. So effectively, we're getting smaller and smaller. As you get even higher at 1 megahertz, you're now effectively pulsing twice as hard as you were before. So if you see in the literature, you'll see some people when they report their pulse widths on their experiments, they'll say that it's the pulse width on the liquid, or effectively zero. So if you take and you put a solution of water when you're doing O17 and you calibrate your pulses on that, and then you put your sample in, which has a very large CQ, you will no longer be at the correct nutation frequency. You'll have to adjust by whatever it is. And in a case where this is true, which is most of the time, you have an effective frequency. In the case of this, 3 halves, it's 3 halves plus 1 half times the omega one or mu one that you're putting in. So for a spin 5 half nuclei, it's even stronger dependence on this. So it's very important that you have an understanding of this practically when you go to pulse on your nuclei. This is why I said, well, we think it's a 90-degree pulse on our sample. We put it in there. We hope it is, but sometimes we're wrong. So it's important to actually check your nutation frequencies with quadrupolar nuclei just to make sure that you're actually in the regime you think you're in and you're not in some in-between space. Okay, so we want isotropic spectrum. Yeah.
Just, I wanted to echo something that was on the last slide that, so, I mean, maybe this isn't something you guys are gonna do soon, but this is such a practical point. And I was reading a little bit about this, and it really can be thought of as you have to include that quadrupolar coupling during the time of applying the pulse, something that we're just so used to turning it off with the assumptions we're educated from solution NMR first. But what's interesting to me, and that I didn't really go through the details to understand it completely, is that now when you get into this limit, that you can't ignore it because omega one is so much weaker than omega Q. There's a relationship to the value of I, like where you end up, where it asymptotes.
Yeah. But
you don't really get a full nutation cycle, right? Because you start to have a very lossy situation also. You don't recover all the magnetization. Isn't that true?
It can get to that point.
But not necessarily.
No, not necessarily.
So you might see a proper several cycles.
I don't know.
Funny
I don't
frequency.
know I don't know if you'll get more than 2 or 3. Certainly not. It won't, be like spin 1 half where we can just keep going and get. I don't know if you can get to the, you might be able to get to the 810. You can definitely get, through 360 and further. But I don't know if you can get to the sort of, 810 kind of pulse that people will go out to when they look at
Interesting.
how good the.
And I don't think integer spins behave the same way.
No, this is only the central. This is unique to the central transition.
Yeah.
So because the integer spins don't have a central transition, they have first order quadrupolar effects, and then
It's just a
everything's
different
out the
story.
window. So this is only true of half integer spin nuclei. So you have an effective nutation frequency that's stronger than what you could before. So now suddenly our probe is working much better than we thought it was. So we're able to acquire much stronger pulses than we were before. This is the glass half full.
If we blame all the problems on the probe, then we have to celebrate the probe if things work well.
Exactly. So
I like that.
Okay, so we want isotropic spectra though, because we want to be able to see things. So we're going to need a bigger magnet. If you want to get isotropic spectra, let's just put it in the biggest magnet we can. That's what they did here. This is done. This was done years ago on one of the series hybrid magnets, one of the Keck magnets at the National Magnetic Field Lab. They took, and aluminum 27 is a spin 3/2 nucleus. And they took spectra at 40 Tesla or about 1.7 gigahertz. And you can see that they're looking pretty isotropic there. They're broad because it's an aluminum. It's just a broad, glassy sort of substance. So it doesn't have, it's not like a crystal that has really sharp lines. In general, it has a lot of degrees of freedom in that packing. And so you end up with broader lines just from the orientation of the molecules in their unit cells, which they don't really have because it's more flat. So that's just why they're broad. But as you get to 40 Tesla, aluminum, it's a 3/2. It has relatively moderate quadrupolar couplings on the order of, 3 megahertz a lot of times, even less. So it's favorable in this case that you can see this. At 14 Tesla, you can see that there's these 4 peaks. They have shapes to them, patterns with obvious turning points.
Yeah.
They're gone at 40 Tesla. So now we just need a really big magnet. But
Look nice, right?
we don't have that much money. So
You've heard
now it's gotta
about
be
this
clever.
magnet lab already, right?
Yeah, yeah.
Maybe because you went to the winter school or something, because I don't think we talked about it in this class. No. But they're interesting magnets.
Yeah, so this is it at Florida State. There's the National Magnetic Field Lab. They have these.
This is the highest one ever, 40 Tesla.
40 Tesla. I don't think that one's still online. Obviously, it's very expensive to run. They're electromagnets, so they're constantly powered. Currently, for NMR, the highest one that they have there is 35.2 Tesla, the new series hybrid. So that one runs high resolution, even NMR. This 40 Tesla magnet, they could do this because they're broad lines, but they probably couldn't get much narrower lines than that because of the vibrations generated by the magnet itself. Because it's being constantly powered. The coil is, being powered. It's an electromagnet, so it's not persistent like our magnets here. It's powered. Okay, so what else can we do? We have to be clever. Let's exploit spatial symmetries instead. We did this already. We can imagine some geometry that exists that can average both the second and the fourth rank. How are we going to do that? Well, we could do them both at the same time. So we could put a rotor inside another rotor and we'll spin them both. This is the double rotation experiment, or DOR. You've probably learned NMR spectroscopists love acronyms, so this will be another one. Double rotation, so we can spin them at 2 different angles. Here we're spinning at 57.74 and at 30.56 with respect to that. We spin them both. So you have basically a rotor that sits inside another rotor, the sample's inside that one. You can imagine some of the problems with this. It's mechanically very difficult to imagine. They've built them. They commercially were available for some time. You could buy a DOR probe. It was a 14 millimeter diameter outer rotor with a, I don't know what the inner rotor, do you know what the inner rotor was? I know the outer rotor is 14 millimeters, but obviously you're stuck with being able to spin what you can spin at 14 millimeters. So you're stuck with a kilohertz or 2 of MAS spinning frequency. So you can see here.
They look like,
Yeah, they're
10
huge.
mil beakers.
Yeah. The 7 millimeter ones are pretty big anyway. So you can see all of the spinning side bands that exist. That's all of these peaks outside of this one that are labeled with the stars. Some of them are inverted. That's for reasons that are happening because of the double rotation. We don't need to get into that. You can read about it in the paper, in Ivo's paper if you want, from 1988 when they did this. So then, the next thing, and this is coming out of, Alex Pines' lab. They did this. They did the next thing. So what if we just spin at the 2 different angles at different points in time during the experiment? So instead of spinning both of them at the same time, let's do a different experiment that's slightly less onerous on our engineering skills. And we'll spin at 2 different angles during the experiment. So that's this experiment, or DAS, or dynamic angle spinning. So we're gonna sit at one angle, and you'll notice that neither of these angles are magic angles for D or G. There's a reason for that. It's because you don't create the echo at the same point in time during the 2D, it actually moves in time. So instead of creating an echo that happens, at time 0 every time, that's modulated in some way, like we think about when we do sort of rad experiment, where you do a carbon-carbon correlation experiment, your echo isn't moving out in time in the same way that this is. This is actually moving along a time axis that isn't the same as T1. So you're moving T1 and the echo is actually moving not just with it, but at a different time constant. And in this case, they chose the angle so that your scaling factor here, is 1. So that's why they're 37.38 and 79.19 and not, 30.56 and, 57.74. But basically, it spends as much time here on this, phase diagram where you have the two rotor angles described, the P4 cos theta. These are like the, the C4 and C2 symmetries, but spatially looking at it, the same amount of time up and down, and it creates an echo on both of them at the same time. So that's why these rotor angles can't be the magic angles, because then you'd end up echoing not at the same time on both of them. We need to echo at the same time on both of them. And then this moves in time out during the experiment, and you actually have to perform an affine transform spectroscopically and processing. Something we could talk about. I didn't put it in anything. It's called affine or a shearing transform. You're basically your spectrum, instead of you think about your spectrum like this, you have T1, T2, T1, and you Fourier transform it and you get F1, F2, and that's perfectly good, and everything's your peaks are like this in that space. In the case of something where you do shearing transform, you end up like this, but you have sort of this space where along this axis is actually the ISO. But that doesn't do us any good, because now our spectrum looks like this in space. So what we can do is we can take and shear the 2D space so that the ISO is up there, and then our spectrum looks like this in space. It's a trick in signal processing, but we can go through it more in depth if you want to at a later date. It's not that important. So what does this look like in practicality? Well, row 17, here's a couple of them that have been done in, looking at MSG. Here's the MAS spectrum at 600 megahertz. Obviously, there's not much information you can glean from this. It looks like just like one really, really broad lump. If we rotate it at 2 angles at the same time, we get this. Really important when you do DOR that you spin at multiple spinning frequencies, so you can be certain which ones are your sidebands and which ones aren't. That's why they've pointed them out with these stars. So they spun at 2 different angles, so they knew exactly which ones were actually their isotropic axes. In this case, looking at cosite, which is just a polymorph of silica. Here, they identified all 5 of these different oxygen using the dynamic angle spinning experiment. In the case of the experiments that I did as an undergrad, I did magic angle flipping. It uses the exact same probe as a dynamic angle spinning probe. You spin at the magic angle and then at 90 degrees, and you can correlate pure anisotropic CSAs with purely isotropic spectra simultaneously. You can do it spectroscopically as well. There, PASS, MAT, these experiments do a similar thing in correlating sideband order with isotropic shift.
How long does it take to do that flip?
In the experiments we did, it was 180 milliseconds.
And what kind of spinning frequencies would it be compatible with?
We had a 4 millimeter and a 7 millimeter probe of them. So you could spin at, the max, 8 kilohertz in the 7 millimeter and, 14 kilohertz or 15 kilohertz in the 4 millimeter. So there was no restriction on the spinning frequency with the hop. There's only the worry that, it falls out when you hop
Dot,
to
dot,
90
dot.
degrees. The bigger problem with that is the technical difficulty of detecting the spinning rate. So the probes that I did had no spin rate detection.
Could you do it acoustically in principle?
I mean, yeah, I knew if it was spinning because you could hear it.
No, you know what I mean, like you put a
I
microphone.
don't know. I don't know if you could. That's an interesting question. It always became the problem of how do you, fiber optics are not, or they're, flexible, but when you're moving that many degrees in that short a time,
Yeah,
even the idea of, how do you even get them in there so they're looking at the right place at the right time? You put them on the rotor or on the stator, you're going to snap them. So yes, we operated by looking at spinning sidebands to figure out that we definitely were, and then knowing, the pressures,
mhm.
the manual pressures that put you at the right spinning frequencies. Okay, but we're NMR spectroscopists, not engineers, so let's just use the spins instead. Can we do that? And actually, Lucio Friedman found a way for us to do that because I don't want to spend all day building things. I want to do some NMR. So there's a way to do this using just spins. So we're going to ignore the spatial symmetries now. We're just going to spin at the magic angle. And now we're going to excite forbidden multiple quantum transitions and see if we can echo some anisotropies away. One of the issues with this is that it uses formally forbidden multiple quantum transitions. So your excitation efficiency is very low, on the order of a few percent of the initial signal is what you're going to be detecting. That's about as good as you can get. There's another experiment called satellite transition, magic angle spinning, that uses allowed satellite transitions, but it's incredibly sensitive to your magic angle. Needs to be set better than 0.01 degrees. So it's,
Now, those transitions, like
Yeah.
if you were in the high field limit, like if the quadrupole were small and you were still really, your state vectors were strictly allowed, then they wouldn't be allowed at all. And I think the
Right.
fact that this works to 3%, it's exactly because of the challenge that
Right.
the quadrupole is large, and so you don't have
yes, yeah.
high field approximation.
Yeah, high field approximation doesn't work, so then we can hit the formally forbidden transitions that are there, but they create us some problems. So this is what the sort of experiment looks like. You really only need 2 pulses. The third pulse just helps with detection. It just echoes the central transition so that you can detect phases better and you don't miss anything. As Anna was saying, with these broad lines, the first few points are really important. Sometimes you have pulse ring down. Sometimes you just have, particularly in older spectrometers, you had inherent delays that you had to wait no matter what. It was just easier to add an echo, then you don't have to worry about that, 10 microsecond delay that your receiver has just to turn on and start acquiring. So you hit it with, this is 3Q MAS, so you're hitting it with a triple quantum excitation pulse, and then you're converting with the triple quantum conversion pulse after waiting some time. D1, and then you have a tau time for your echo delay, and then you echo your P1 pathway, and then if you follow the C0 and C4 diagrams, you'll see that they actually echo out here in time because of the way these pulses move them. Sort of when their positive and negative characteristics add up, that's the time at which you echo. So you actually are creating these echoes in these pathways. So therefore we have a way to make a 2D experiment where we're echoing out an isotropic dimension and time. This looks like this. This is what I was talking about with the affine transformation. So you end up with a T1, T2 diagram when you're doing this, where what we're interested is echoing these out. We've gotten rid of everything but the C4 pathway by doing MAS, if you recall. So we did MAS. We're doing magic angle spinning at 54.74 on the D pathway. So instead of caring about sort of this P echo or this C0 echo, what we're really interested in is getting this C4 echo along T1. And so we can do that just by basically shifting the spectrum or shearing the spectrum up to that point. You can also do this in time by editing your T1 time in between here such that you're acquiring at the proper time in each point. So those are called shifted echo MQMAS, and a lot of people, that's how they acquire them, so they don't have to do this post-processing piece. But this, there's a scaling factor K here that defines what the slope of this line is in space. And it, is proportional to I and some other things. So it matters which, and whether you're doing 5Q, because obviously triple quantum MAS or 3Q MAS of the MQMAS experiment works for all spin half integers, but on oxygen you can also do a 5Q MAS on other ones you can do 7Q or 9Q, and the higher the Q is, the narrower the isotropic spectrum is, but the lower the efficiency that you have is, because hitting that 5Q transition is even harder than hitting the 3Q. In general, these pulses need to be incredibly hard and incredibly short. So similar to like the deuterium experiment, you want, sub 2 microsecond, 90 kind of pulses on the strengths to eke as much sensitivity out of them as possible.
How do you select the free band of these pulses?
What?
Based on the transition you want, you select the free band of these pulses? Or?
So you optimize the length of the pulses. You optimize, just empirically on the experiment itself. The way you select the pathway that you want is by phase cycling.
No, they're not 90 degrees.
No. No, they're not 90-degree. You optimize them by running the experiment and seeing how much signal you have in the 1D. And they'll be dependent on, the nucleus, the spin, and the CQ of your sample. But the way that you select it, you're only seeing the triple quantum pulses is by phase cycling. It's not like you pick this pulse and you only get that just by doing the pulse. You get single quantum excitation as well. We just filter it out by selecting only the things that go through this P pathway. Oh. Okay, and as he's brought up, we have an isotropic frequency term that doesn't come from this chemical shift, and in these instances, isotropic frequencies are not chemical shift. They're just isotropic frequencies. They're a linear combination of chemical shift and quadrupolar isotropic frequency. Therefore, we have field dependence of our isotropic shift. So if we take, in this case, this is DAS of rubidium 87 and rubidium nitrate. There are 3 different rubidium nitrate sites in the unit cell. So you have 3 different peaks. If we take it at 4.2 Tesla at low field, there's where the 3 peaks are. You can see that they move on the spectrum, on the frequency spectrum, as we move up in field. And if you plot it over here on the right, you see that they have different slopes, and there's actually 2 of them that cross in those experiments where the rightmost, this peak at -70 ppm, it is over here, and then suddenly it's actually on center by the end.
We should find out about the electric field gradient in the selectivity filter. Rubidium is a good nucleus for KCSA. KCSA likes rubidium.
Well, I mean, rubidium is an excellent quadrupolar nuclei if you wanna look at it, because it's favorable with CQs. It has fairly small CQs.
And
What about K39?
Big CQs. Big CQs. Rubidium 87 is also very sensitive, like higher gamma, potassium lower gamma, high CQs.
I'm pretty
So-
sure that that's true. We have to double check, but I think this ion, it does okay in the selectivity filter.
Yeah,
And then, you remember this, okay, so, and then you have, some scheme by which you have to eliminate the solution peak. So you're just looking at somebody who's, in
That's the problem.
the selectivity filter. And you don't want it necessarily moving through. You
Yeah,
want it-
every time that I've thought about this experiment, I always get hung up on that. How do you get rid of the solution?
Because if we're gonna
That's always
drop
the
the
thing.
temperature to make it sit still in the selectivity filter. Or even does it?
I mean, the way to do it is correlation spectroscopy, but we're not there yet. In the lecture. That'll be tomorrow.
We're gonna organize this experiment. This is exciting.
Okay, so anyway, so that's just an important thing to note is that if you're ever going to take spectroscopy of quadrupoles and you're gonna do isotropic resolution, don't label your spectrum chemical shift. Label it isotropic frequency. It's not chemical shift. There's other contributions to that because of the second order quadrupolar.
But at a high enough
Interact.
magnetic field, I would create depression.
Yes, if as at the limit that I think I might have read them the wrong way around, but anyway,
Yeah.
yeah, at the limit that, mu q over mu omega is 0. So,
Which, yeah.
for a large enough CQ, it might be
Yeah.
infinite. Okay, so then I don't know how much time we have or when. So I don't want to keep everybody forever. We have tomorrow too. It's not a.
What do you guys think? Do you want to take another few minutes, 5 minutes or something, and then, is that all right? Are you guys flexible?
Yeah, okay, so just some practical aspects. We're gonna talk a lot. As I go on tomorrow about oxygen 17, so I'm just gonna talk specifically about oxygen 17. You have about a 400 ppm chemical shift dispersion in biological oxygen sites. So here we have, sort of the CO of a just a carbonyl. Well, this is the carbonyl. This is just C double bond O. If you have the two, this would be the one of the carboxylic acid. This is that second OH. This is just a hydroxyl group, and then you have water. And so then if we break these out, you can see this is just taken from a review paper where they, published a bunch of the different chemical shifts. If we just break out each one, so the hydroxyl groups, you can see the different individual ones there. So even within that, you have a 80 ppm dispersion of hydroxyl groups. The carboxylic acids and the carbonyls. You have similar large 80 to 60 ppm chemical shift dispersions in this. So practically, this is an excellent nucleus. We have very good chemical shift dispersion. Unfortunately, at 500 megahertz, if we just have one of each of those sites, spectrum is almost uninterpretable by eye. Certainly, we can fit this. If we know there's only 4, say we think there's 24, it becomes a much more difficult problem. Even at 700 megahertz, we still have a problem. even at 900, there's still overlap between, you know, 2 of the 5 different sites. We have 5 different sites, but 2 of them are still, we still have 2 overlaps. When we get up to about 1300 now, we get resolution of each individual powder pattern on its own, without that. So this is sort of a bound, this is, you know, sort of frozen water, bound water, so it's not isotropically tumbling, something that might be, you know, in a crystal or hydrogen bonded to a protein would have this sort of shape. And this has DQ of approximately 7 megahertz. So
Now,
then
this-
something like this, like 9 to 10 megahertz. And these ones, again, right around 8.
This axis is the total shift, including the second order quadrupole and the C chemical shift.
Yes,
And the functional groups at the bottom are what that total shift would be for the
That's
high
the-
field.
that's the range. No, this is the range of chemical shifts that have been reported by, so the chemical shift is determined by fitting using, you know, Simpson, some, you know, program. So these are actually the reported chemical shifts for this
Ah.
range. So you'll notice that if you look at this, this chemical shift, like I've just plotted a single individual one above. But that, you know, this chemical shift range is here to here,
Mhm,
but this orange spectrum, you know, is here on this one.
mhm.
It goes over to here. Now it's like over here. Now it's like all the way over here. So what's going on? You know, this is way outside that chemical shift range. Well, the chemical shift is just a single instance in this in time. So how do we interpret this spectral fitting? You can use multiple different types of programs. You can use a full spin system simulation in the time domain, something like Simpson or Spinach or Spin Evolution or Gamma or Pi Gamma. You could write your own if you want. And you can fit them using that, or you can fit them with a program specifically designed to replicate the frequency domain signal. There's equations out there that tell you what the frequency domain signal of these types of tensors are in their shapes. There's a couple of programs I just wrote down there. All of the different programs, their papers are there. So Dominic Masio with DMFit, this SS Snake does the same thing. And it's incredibly helpful to have multiple magnetic fields, just like any sort of wide line pattern. Maybe not deuterium, but for CSAs, it's helpful to have multiple magnetic fields because you end up with assistance in the changing shape at multiple magnetic fields because the second order quadrupolar interaction is field dependent. So its effects on the spectrum are different at different fields. So it's helpful to have in the second field to nail down your fitting. Okay, so what does this look like? We'll cover this and then we'll be done. Just because we were talking, I pointed out this isotropic thing. So here is a paper that I did sort of at the beginning of my PhD, where we looked at oxygen 17 and bound water environments. Water is bound to amino acids, so monohydrates and dihydrates of, you know, single amino acids, and then a couple of di amino acids, gly and gly. I mean, I've just plotted 3 of them over here. We reported chemical shift dispersions. This is the first time looking at chemical shift dispersions of bound waters with oxygen 17, around a 40 ppm chemical shift range, you know, like 33 or 34. The one interesting thing that we found was that all of them had near identical quadrupolar couplings and asymmetry parameters. You can see them here. They're all right, almost exactly 7 and almost exactly, you know, 0.9. You can see them in the shapes. They look very identical. So this is just pointing out that unlike patterns that you think about in terms of, you know, CSAs, the isotropic chemical shift is not the same as the center of gravity chemical shift on a residually broadened second order quadrupolar interaction because of the quadrupolar isotropic frequency. So you can see that the isotropic chemical shifts are happening near the left edge of this powder pattern, always. So in general, your isotropic chemical shift is going to be toward the left turning point, you know, of this pattern.
Is that because of the sign of the quadrupole?
Yeah.
Yeah.
For oxygen 17. For other ones, it'll be, but sometimes you'll see people, if you have a quadrupole that you can't fit, maybe it's too broad, it's just a broad peak, they'll report instead of ISO, like delta ISO, they'll report CGS shifts, center of gravity shifts. And that's because center of gravity you can just measure by integrating under the curve and just putting it right in the center. And then you can report that, and you don't know that it's definitely the isotropic shift, but you at least know what it is. So we can pick up tomorrow with why this is interesting that they all have near identical CQs and eta Qs.
One quick
Yeah.
question, what was the pulse sequence?
This is just these are just acquired with the Han echo pulse sequence.
Meaning 90 tau 180? or-
Yes,
Oh,
at 90 tau 18.
So that's an effort to refocus just the central
Yes.
transition. And I imagine there might be some caveats. I see a lot of papers where they have composite pulses instead of
Yes.
just the 180 or whatever.
Yeah, so this is just simple. We're not looking at something that's terribly broad. I mean, you can see here that these were acquired, I want to say at 750 or 900 megahertz. I don't recall exactly now, and I don't have it here. I can look it up, obviously. But, you're talking about, from, minus like 30 ppm to, about 40 ppm. So you're talking about 100 ppm. It's not so broad that you can't think about that full breadth being excited by just a regular pulse. But there's all kinds of, I'll talk a little bit about that too. There's all kinds of fancy techniques to try to do to excite wider line spectra that are used in CSA cases, things like platinum or lead, that have massive 1000 ppm broad CSAs where you can't excite the whole spectrum, even in an MAS spectrum. So these are just in a 20 kilohertz MAS. So you're not spinning really fast, but
Great. So just,
Yeah.
I mean, I know you want to talk about a lot of this stuff tomorrow, but that is something that would be possible with a standard MAS probe, but it would be good to go to the highest magnet that we could go to.
yes, yeah,
I mentioned when I saw Chris Juraniak recently, he was here for Hashim's,
Yes.
and, he was really emphasizing how it's gonna be very soon possible to go there and use the instrumentation there. So there are various places that we could go to do a higher field
right.
study, if that's what was needed, maybe get our act together on our 900 here and then go someplace.
Yeah, I mean, there's certainly opportunities for that aspect of, running it there at the National High Magnetic Field Lab.
do we have like any probes which are tunable dose empty?
Yes,
So
yes, so we have, in-house, we have two currently. I guess 2.5 we could say, because one of them has two different probe heads. But on the 900, we have an HFXY probe that is tunable to oxygen. It is likely even tunable as HCO. Have to double check that. Probably not tunable as HON. That's a really hard nucleus combination. Nitrogen and oxygen are pretty close to one another, so it'd be very difficult to get that tuned properly. And then on the 600, we have a DNP probe that's HXY as well, that will tune to oxygen. it's a 2.5 millimeter Phoenix, and then 900, it's a 1.6 millimeter, with a E-free foil or a 1.2 millimeter, just regular solenoid foil probe. Other than that, we have 4 millimeter, HX probes on 750, which can be tuned to oxygen.
Why can't those 70 be NP?
Yes,
Okay.
And supposedly the other thing in the selectivity filter is a water molecule, right?
Exactly.
But we have to think about maybe the only strategy is like a dynamic filter set type strategy, right? Like there are some temperatures where the one in the filter would be more mobile than the one in the ice, and there are other temperatures where the one in the ice or the water would be more mobile than the one in the filter. We'd have to
It
do.
might be more used in the water behind the filter, in the water behind the filter,
oh, the ones that
So
are.
asking the
with
question,
The
yeah.
contacts
yeah.
on the backside.
Yeah,
So if there exists a water molecule that has a very slow off rate, that has some binding site and it has a slow off rate, would we see all the O17 as being a solution and a more signal, very different properties, and then just one or two sites that look like solid water? And I mean, this must have been tried on other proteins already. Not that you know
Not
of.
that I know of. That was always the proposal. We wanted to, so all of this work, I'll go through my other papers, but 17, all of this work was building up to the idea of, so one thing that I didn't know, and maybe it's important to just caveat it right here, is that, if you recall back to Anne's slide of, I think she had a slide where it talked about the, maybe it wasn't one of the ones that she showed in the periodic table. Maybe I can show it more of how much, what the natural abundance of these things are.
Yeah.
Oxygen 17, 0.037% abundant.
It has to be easy to get it into whatever you
Yeah, so
want
you
it
have to be
in.
able to,
yeah.
label, which is the hard part, and it's expensive.
Yeah.
So,
And especially O17 water could be the easiest
Thank you.
starting point.
That gets you thinking though, it could be super interesting, right?
could be.
At least try something.
I've definitely thought about it before. Okay, I think we're done.
I was thinking.
Thank
about
you. Super interesting.
I was thinking about it